Hi, my name's Bob Greener and I'm a volunteer with the Martin Fleischmann Memorial Project. So hopefully I'm a little less tired than I was earlier in the week, and I've got a lot of nice things to show you, some of which I prepared and some of which I'm going to prepare on the fly, as is the way. I'm very excited to share what I have, which I would have liked to have shared in Assisi, but for whatever reason that didn't happen. And I think that we're gonna kind of be in the home straight now for understanding the very basics of how these coherent matter structures, this exotic vacuum object, this itonic cluster, this ball lightning, this ectons, all these kind of things are related. Anyway, just before I start babbling too much, can everyone hear me before I go on? Can everyone hear me? Can anyone hear me? uh, Let me know. Okay, thank you. Thank you. Okay, brilliant. Perfect. Okay, so here is my title slide for the day, and it is Monopoles, Ball Lightning, EVOs, Coherent Matter, Strange Radiation. I don't know how much we're going to get through today. I'm going to throw some ideas out there and seek your views on it. But one of the big reveals today is what is in the left-hand side of this frame. If my mouse will work, that would be great. Over here. And this is part of the Vega Valley sample. And what you're seeing on the top here is an image taken with the Dynolight Edge, and that's this USB 3 camera with a 5 megapixel sensor. And on the bottom is a far more color accurate image taken with macro photography 5x Laura lens on a Sony Alpha 1 and then stack focused. Now, just to let you know that I've got to the situation now where I can pretty much get a one-to-one match between the microscope and the Sony Alpha and Laura. However, the Sony Alpha and Laura it has so much more fidelity in it. But for quick and dirty analysis, the Dynolight Edge gets you the same kind of pixel resolution. If you want to go higher than both of these, actually the $70 attachment for a Samsung F7 seems to deliver quite nicely, but it has good color accuracy, but it doesn't have the measurement capability. And in fact, the actual pixels in this Sony Alpha 1 image here are just under 1 micron across. So it's almost 1 for 1. 1 pixel is 1 micron. And so it's quite a nice resolution. And it almost gives you a good understanding, a quick look-see of what you are looking at. Anyway, this is part of the eastern part of the Vega Valley, as we've described it in the past. And again, on the right here, you can see what I believe is the end of a floodplain on the electron condensates. And we're going to talk about something that I found on here and that was very, very much clearer on the Sony Alpha 1, and how this plays in with the claims of Solin in 1992 in his patent, and also how it goes with what Shoulders said and what we observed on the Sumerian lantern. And this is an SEM that was taken just over a week ago. And there's something also very, very special on here, which I was going to give as a special treat at the conference, but we never got there. And what I want to do is I want to take some higher resolution photographs on here. But if it is what I think it is going to be absolutely epic. Anyway, without further ado, I'm going to talk through a few more slides that I had on the presentation that I gave on coherent matter traveling wave beams, and the second part of that. And I'm going to add some more context and detail to that. And then what we're going to do is, you cannot have imagined how satisfying it was to look at the copper tube that Henk had sent me. Because what you're going to see is everything that I'd supposed was going on at the micro level, and had described in the past, I think we have very strong evidence for that, and I have another microscope session booked. But I think by the end of this presentation, hopefully, and discussion, you will understand really how a ball lightning eats matter, the phenomenological basis for it. Actually, I pretty much nailed it in previous descriptions, but you're actually going to see the scanning electron microscopy, the changes in elements, and the progressive consummation, I don't think that's the right word, consumption of the fuel, which is just whatever you feed it, basically. And so I think this is going to be really, really exciting. And we're going to refer back to previous work on the line reactor, because this shows how the monopoles can cluster, and then that will guide us to what we are seeing on the Vega Valley. So this is when everything's coming together, and you know, when you're going in the right direction, and you know, everything will line up, and whenever it's replicated in the future, it will do the same thing. And this is what Piantelli said, like, it's not science until it's all self-consistent. And I think we're approaching science here, and it's great to have been able to go through this journey with you. And thank you, Dave and Henk. Dave's tracks that you're going to see in this video are absolutely mind-blowing, and I believe that they are most, if not all, and certainly if I haven't dug out some that fit other strange radiation tracks, then we are going to be able to find them. I'm pretty certain of that. And I'm going to be looking at those with natural ball lightning that does not occur when there is a ground strike. So this is ball lightning that occurs in the air. And so we can discount the Abraham Dennis model and the whole sort of silicon discussions around that. And I think it's going to be... It is a complete honor to be able to share this with you. And then I'm going to talk about what I showed at the end of my third presentation, the very impromptu presentation that I had to give to a small audience. I don't really want to go into how that came about, but I did my best to get across the warning. But also there is a silver lining, let's put it like that, to that question of safety. And I think when people understand what I hopefully will get onto today, people will have a better understanding of how to target particular nuclei in their synthesis. So it's all very exciting. So thank you for being with me today, and I shall get going on the review of the previous slides. So this is the slide front cover, and I've just thrown on there some of Dave's absolutely stunning tracks. He sent me a video and said, I think there's some things in here. And so I painfully went through frame by frame by frame and found, yes, quite a lot. And we're going to talk about these. And before I do that, I'm going to close the window because there's a lot of noise outside. Okay. Right. The one at the top here I particularly like, and we'll see this again. And what you see, and this is very important, there is a break line here, and there is a break line here. And what these are between frames. So I think this is either 30 or 60 frames per second. I can't remember offhand. But it's kind of like there is a break, and then the camera turns on again, and this is the gap between the frames. And you'll see this on many of these examples, including the ball lightning that was captured by AID in the outback of Australia. And so when the ball lightning in that case is traveling and it's several miles away, there's much more breaks in the footage. And so you need to kind of extrapolate through. But what I like about this one is it kind of speaks to what Leclerc was talking about when he thought his water crystals were creating something that was akin to DNA, because this is actually a double helix, and it almost has base pairs, or whatever you call them, between the two helix with dark gaps in between. It almost looked like a 3D model of DNA, and one wonders whether that is actually what may have brought it about. Anyway, so that's the one in the top left. In the top right, we've got somewhere between an M and a hat. Wonderful, wonderful trace. In fact, there's a much longer sequence of this. So this is actually just what was caught in one frame. And what you can see here is JPEG artifacting caused by the camera. So there's a block around here. So what we would like, what we have to do really, is to use camera technology that is not doing this level of compression, but gives us the same fidelity and frame rate. But 90% of what you want to see is probably in these frames that I captured from Dave's work. Here is the classic M&M track, which I always, well, many people in this field thought was impossible to imagine how it could occur, and there it is. It's doing it, and you know, it needs to be explained. Here's the sort of bouncing sort of ball ripple thing, and here's another one that's much more broad than this one above here. But again, the two sides of this, you know, I hear a lot of people in their heads going, Birkeland current, Birkeland current. The two sides of this seem to be tied together. And in fact, when ball lightning splits up in the air, it seems to have these bands going between them. There's communication between them. And actually, I mentioned in my presentation that this actually occurs with Ken Shoulder's work. He described going through two dielectrics. If it didn't fit, it would split up into multiple little balls that kind of bound together. And when they came out of the gap, they would then rejoin back together. So absolutely fascinating. Now, towards the end of this presentation, we are going to be again referring to this Matsumoto Itonic cluster mesh and the replicated structures that we observed on the cavitator of Dr. Ruishin Amasa, and how important this is. And my intent is to get to the special treat, and I did show one in my impromptu sort of workshop in my third presentation in Assisi, but I'm going to actually show you one that I showed in 2017 in Copenhagen, which I thought was very curious at the time, and I believe that that is also the output product from a dead coherent matter traveling wave beam, and because of what it is, I think it's going to be very interesting for its implications. So I talked about these things which were references, and you should look at the great work of Lutzi Eitner. Lutzi Eitner is the guy that ICCF22 calculated that within the torus of an EVO, or a condensed plasmoid as he prefers to call them, he, as a nod to Winston Bostick, the pressure in there is equivalent to, I think it is 5 times the center of the sun, or whatever it is. It's 5 orders of magnitude, maybe one of those. It has 50 million Teslas, and so that's very magnetic, one can conclude, and that it is equivalent to the center of a pulsar, which is a type of neutron star, where obviously nuclear reactions are expected to occur. And then Edward Lewis has done a great work on safety, and actually part of the main thrust of getting to the point that I made in Assisi was there was a lot of new people, well-funded, coming into the field, and as long as they weren't successful at producing excess heat, they probably were going to be unlikely to harm themselves with strange radiation. But I think I made it very clear by demonstrating with the one experiment by Roitskev of the exploding wires that ball lightning, transmutation, strange radiation, and magnetic monopoles, and the changing of spectral bands of light are all absolutely inextricably linked. They are all part of the same phenomena. And this one here by a review of myself of Alexander Parkhomov's strange radiation tracks. These are outside of the reactor, and they are interacting with things like boron nitride, which is in hardness terms it's second only to diamond, and in other very hard materials. So that is always worth looking at. Just briefly, this was the kind of first time I saw something that looked like it was somewhere between a laser and a maser, and I mentioned that before, and I think because of that it forced Anatoly Klimov to release this Soviet era, I believe, research, or certainly 1990s, and I've done a lot of videos on this and people can review that. So we won't go into this video, we showed it in the day, but what we will do is the next slide, if I can get to it. this one here. This will become important to what I'm going to discuss today. And what I'm referring to is the way that the ball lightning, the coherent matter, these balls of fire, these tufts as the Sapphire group likes to call them, how they self-organize, and they tend to go onto facets of surfaces and self-organize on those facets, or they go on to tips. Okay, and so there's the video that I discussed. And it came about some time after that there were these squiggles in Henk's particular experiment, and Dave went ahead and replicated that, and it went very quickly to extreme interactions, which I've reviewed in the past before, where they ignore the cathode and anode, ignore pressure waves, interact with dense material, large changes in direction and speed. They split and merge with the divided segments showing the same in-phase structure, and they interact at a distance and in anticipation of interaction. And so I walked through a number of things that I've talked about before, and these were the early observations of tracks that met previously observed, or not even observed in the case of this one by Ken Shoulders. It was just in one of his micrographs from some of his previous work. And now here we're talking about some other kind of, this is a still frame from a video, and what you're seeing down here is one frame captured. And what I was describing earlier is that the gap between two frames, in this case it's actually missing a whole frame, so that the actual the shutter time is only open for 180 degrees of the frame time. So actually there's a whole gap where it's missing a segment in this particular one. But you can see how it's slicing it off, and if it was doing it open for the whole frame, then you would still see a black band. There's just a slight gap in between the frame sampling. So that is just what there is. There's actually another spiral one over here, but you can see its velocity is much smaller. And then there are these squiggles, and just ones that more look like kinetic particles over on the right there. Okay, so this is what a typical video will look like if you're just trying to, that was it, right? And from this video that you've just seen do that, we've got these tracks, and they are rather fan-dabby-doozy. So this one down in the bottom here, it looks like it's got something running through the center, and it's got two things spiraling around the outside. This one looks like a double spiral, like this one here, and like this one. This one's this DNA track type one that I was talking about earlier, and this is kind of an extended version. This is the kind of M&M track, which I rather like. Get rid of my mugshot so you can see the whole frame as it should be. Some nice tracks, I call it. And I love this one because it's either coming from up here and going round here and going round here and down here, or it's going round there. But, you know, if you saw this ordinarily, you might think this is absolutely, completely bonkers. But it looks almost like Celtic artwork, I have to say. You know, maybe Celtic artwork was inspired by observing this technology being used. But that's pure speculation on my part. But anyway, what I can say is that having done the extreme interactions video, people can understand that these kind of things are perfectly possible with these structures. Now, the next slide is absolutely wonderful because it shows some spectacular examples. And so at the top here, I think this is a standard toroidal Evo, and it's just making a pipe. And this would be the sort of one, in my view, that would go through, it would go through your material, and it would leave two parallel lines. And if you looked close up at those parallel lines, you would have a helix going one way and a helix going the other way, because you're seeing the toroid going, you know, 50% in and traveling through the material, and it's got the counter-rotating pieces on there, and so as it cuts through, it leaves that kind of mark, and you know, that was discussed in my impromptu session. Now, the one on the right here we'll discuss with respect to a very old documented example of natural ball lightning where there is some sort of squiggly waviness, and this is almost like an M&M track but on the max, and then it comes up to here and it kind of like something goes inside itself, and then it just fires out this beam, and there's nothing in the next frame. It's kind of like something's happened, and has it disappeared? I don't know. Here's that full kind of semi M&M track, and you can see that actually as it comes out, and you've got a segment of frame. Oh no, I'll go back. And you've got a segment of frame here, segment of frame here, segment of frame here, and so on. There is some periodicity changing, and so is it losing energy, or is one of the beams sharing its energy with the other? Because we observed that on extreme interactions. There seemed to be some desire to becoming in phase with the other stream, like so they're like merging as one. And you do see this on strange radiation, where they kind of change behavior part the way through a track on the historically observed ones. Now, this one I think is absolutely fantastic, because you've got your blown plasmoid, your macro ball lightning here, and it's coming out and it's leaving these kind of bizarre kind of dark bands, and it's slightly wavy. It's it's almost like a candy rock or something in the way it's going. And this is I only saw one of these in this particular video, so I'd like to see more of these. So Dave, thank you. If you can send me some more of your hard work, that would be great. This one I can't be sure whether it isn't three coming together, but as I said before with this one, and as we observed in extreme interactions, it seems much more dynamic down here, and then it seems to be coming into a more coherent beam itself until it's got less wiggles on the outside, but it still has some substructure to it. It almost looks like it's 3 or 4 maybe running together. And again, what you see here, maybe you can't see it, I don't know, but you will have the slides, and I will publish these and put them into the blog at remoteview.acu after the presentation. But you can see a break here, and there's a break over here, and I think there's even a break in here, but for some reason it isn't showing it quite so badly. And most of these you will see a break. Now, the one that is absolutely spectacular, the scale of this is phenomenal comparison to many of them. In fact, there was 2 in this particular video of this type, and the only thing was that this was longer and it came towards the camera, and so as it's coming towards the camera, and the perspective is making it look like it's stretching out. But the wonderful thing about it is you can clearly see the structure in it. It's just absolutely beautiful. And you can imagine this if it was going 50% through a surface, how the intense energy in these outer areas would cause the destruction of the surface in a particular form. And that's true to say of all of these. Now, the next one is a little bit controversial, and I would like to maybe have some more examples of this, but it's certainly something that Ken Shoulders said is possible. And considering many of these tracks in the Vega reactors don't seem to be responding to the electric field in there, like they're not electromagnetic, they're sort of don't respond to the E and B, they are in their own little world, interacting with each other like they are scalar and vector. This particular image, I think, is in this next slide, is very, very interesting. So let's have a look at it. So, and the reason I'm saying that is because Ken Shoulders said that they can go through metal. And this is actually one frame, and this is the plasmoid or the macro ball lightning, the coherent matter that may have collapsed, and we'll discuss that later. And you can see the double spiral coming out here, and it looks like it enters the corner of this piece of metal, and it kind of comes out halfway through the metal down there, like it actually went through. This, for me, is something I'd like to see some more examples of before I'm confident that that is what's going on. But if that is the case, then it lends itself to the idea that these aren't necessarily glowing because they're hot. It might be that they're glowing because they're condensing, but that they are able to travel through material. And it might be that they're glowing because as they're condensing, they're emitting these soft X-rays, as Ken Shoulders said they did, and it's ionizing the gas around them. It's ionizing the gas around them rather than them thermally cooling. So it's a non-thermal emission of radiation that is stimulating this glow. But the actual body itself is able to pass through solid matter and come out the other side. And as I've been warning the guys doing the Vega experiments from the day one, and actually from the Sapphire team as soon as I could get their ears, is you need to be as far away from these things as possible when you're running them. As Parkhomov said, I think it was in Sochi in 2018, Zatalepin and Baranov said, you know, aren't you worried about all the strange radiation coming out of your reactor? He says, no, not at all. I have it in another room, in another lab. So dilution is the solution to pollution. Okay, so I think this is, for me, one of the more interesting of these slides. Of course, one might conclude that these are all exceptionally interesting. Now, the next one that I'm going to come to after a couple of slides is I'm going to refer back to this one again. But before I do, I've got a still frame. I had a bit of problems describing this, but for those that haven't seen this video before, I would recommend you go and see it on Vega Extreme Reactions. But I think this slide kind of sums up one of the main features. You've got a big ghosty spiral one over here. But this is all one frame, and what's happening here is in this frame a exotic vacuum object is coming over here and going around. It's bending round, and by the way, none of these are seemingly interested in the anode. The cathode's down here, not really interested in the cathode, more than they are interested in each other. So this kind of bends up here to kind of join this one, and then it bends round it, and for some reason this bending round this causes this one to be influenced to come back on itself, and when it comes back on itself, this bends in the opposite direction, okay? And so this is then going along here, and you can see that this is at this point. Now there's another one that's coming up from here in the previous frame. You can't see it because it's in the previous frame, but it actually bends round and kinks round this one before this one even arrives in the position at which this would need to bend round it. It's actually like it's emitting an intense beam of magnetic beam, or that I believe it's some sort of vortex field, which actually may actually be what magnetism is, or maybe some spin field in the cold neutrino condensate. But anyway, there's a number of speculations you can come from, and I know people say plasmoids emit like you know, photons one way and particles the other way, but photons aren't. I would expect something to make this come round. Maybe particles, I don't know, but I think there's something more interesting going on here, and since these things are quite likely to be absolutely chock full of magnetic energy, that for me would be the first port of call. And then there's this structure down here, and in the overall sort of merged file here, there is this structure. And I'm saying that, like Birkeland currents, or like these plasmoids, these counter-rotating plasmoids that Bostic talked about, this and Shoulders talked about positive and negative EVOs. This may be positive one and this may be negative, and you only see the positive track because electrons are attracted to it. Or conversely, it could be negative and the ions are attracted to it, and the ions are more ionized by the condensation that's going on with the track. So it's one is one and one is the other. That's what I suppose is happening. And I think in many of these bouncy looking tracks, it might be that there is the other species, but you just don't see it. So when we were looking at this kind of bouncy track here, it might be that there is the other species, but you're not seeing it. Okay, so, and that's the sequence there that we got all those from. Now I'm going to do some comparisons now between natural ball lightning, one from Hestalen, which occurred in the air, and another one from Aid in the outback in Australia, which occurred in the air, and look at another one from a historical archive type of point of view, and compare them to the kind of things that we've been looking at. Okay, so here it is, natural ball lightning traces versus condensed matter traveling waves. And this one here, if you go and look at my series of videos on what I call UFOs over Hessdalen, Norway, and I have UFOs in quotes because many people have assumed that these potentially are UFOs, but I believe that they show the behavior of ball lightning, and that's probably what they are. But particularly, I believe that they're ball lightning because of these type of traces that they do. So you've got an M&M kind of track along the top here, and in this point here, it hits a treetop according to the testimony, and then it kind of breaks its period and changes. So that there is some causality, there's some sort of interaction that causes this kind of track to change. So like I say, I think we've safely created these type of tracks. This one down the bottom is the trace that I put together by combining the frames from the ball lightning that was captured by AID in Australia, and you can go and look at the video here of that, and in the video there was descriptions to more information and context than the original videos, and the daytime video from as best he could do the same shot, so you can see that it was actually in between a couple of trees where this is observed. And it's quite fortunate because that was in the camera view, and he pulled his car to the right, so then it produced a trace, and he actually kept it in shot. So he was super lucky, but this was kilometers away. Now, one thing to bear in mind with that parallax, there may have been less movement than was captured on the camera, and that there was actually more just spiraling going on, but over a shorter distance. That being said, the kind of spiraling you're seeing here is very similar to we've observed in, even in this one frame from Dave's Vega experiment. The other thing to note is what I was talking about earlier here. There are these breaks in the frame here, 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 here. And again, this is the artifact caused by the frame sampling on and off time. So that's just that artifact. So you can imagine that this is a more continual trace like these are, but obviously these are traveling much smaller distances, and they are much smaller structures. AID describes these structures in a similar fashion to Hessdalen, where they are meters to tens of meters in scale. Now, this one over here, I've talked about this in the past, and this is actually recorded in W.R. Corliss' Unusual Natural Phenomenon, and here is the book that this is recorded in. But you've got this glowing squiggle that comes to a point, and it has this like torus, and then something is ejecting through the torus. And I couldn't help thinking that this was similar in form to this kind of glowing squiggle, which comes down, and then you've got something that looks a bit like a torus, and then something coming through the torus. So I think it is safe to conclude, in my view, and I would like other people to come up with cogent and coherent arguments to counter my position. But I believe that we are creating in the laboratory pretty much all of the observations of ball lightning in the natural world. And here is another one, and there's a reference here where you can go and see an excellent paper by a Russian author that I actually shared the presentation of on the MFMP's YouTube channel last year. And there are these knots, and we described how these knots are observed here in the extreme interactions video that I discussed. And then in the presentation I also went through this grouping, and we've done this before, but I put together a slide here which may be better to help describe this process, and I probably aren't showing this. Am I not showing the images, or have I just got my mugshot on? So I was describing this Corliss one over here, and if we go back, I'm saying that this Corliss one is equivalent to this glowing squiggle that comes down. There's a torus-like object, and then something shoots out the front, and then it kind of disappears. This is exactly what is observed on these. I think it's 1, 2, 3. And then this is the fourth frame, and then there's nothing after this. So I believe that this is the same kind of behavior that was whoever observed this and then it recounted it to, I think it's MacArthur's house. So it might be MacArthur that observed this and was recounted by W.R. Corliss. And so you can see this glowing thing. This is the torus, and then the thing shooting out. So I believe that's the same thing. And I was talking about this ball lightning that's coming down to the ground, and it has these little knots, and we have the same kind of thing over here where you have it coming and there's a little knot, and comes down, there's a little knot, and so on. So I believe basically in these Vega experiments we are showing the behavior of natural ball lightning, and when I talk about the macro scale of the ball lightning and how it works, which I did a little bit of in Assisi, we'll also see that that is playing out on the micro level, and that was the most satisfying thing to see in the SEM session, having kind of visualized it in my head as being the way that these shells are formed, to see the actual, what I believe is nigh on proof, but I want the second microscope session to really delve into these examples and nail that one, let's put it like that. Okay, so what I've done actually on this slide is I've probably made it a little bit easier. I might have got the assignment here wrong to the original one. I believe it might be the one that's behind that then comes out here, because it's the most dense of it, and it seems to be moving a little bit slower. But anyway, I might be wrong, and I might need to correct and update this PDF. But for the moment, you have this ball that expands, and then it ejects this structure. It comes around the top to the left. It then hits the cathode. It gets energized and actually comes back on itself, the opposite direction. Comes down, hits the cathode again, gets more energized, comes round in the spin field of the discharge, and another one is ejected at this point, which I'm marking in green, and it immediately starts orbiting around the original one. And so you can see right here in this image how these things are able to cluster together, and you can see in the next one that the first one and the second one start to become in phase. And in fact, this is what partly my confusion is that I don't actually know whether this is actually become one at this point. I think it hasn't, but I'm not entirely certain. But it looks like this one is this one here, and this one goes to this one here, and then the one behind is actually the original one that kind of for some reason is lagging, and then it becomes this one. But anyway, so the blue one gets joined and the green one get joined by the purple one. They sort of are together for a little while, and it's just amazing how this purple one immediately again starts to orbit around. So in this point, we don't see we see it before and then we see it fully orbiting around it. This one's beautiful because we see it before and then we see it just starting to orbit around it. So this particular sequence of frames really shows how they can cluster together. But maybe it's that they don't like being in groups of three. Anyway, the point being is that there's this little yellow one I'm pointing here, and it comes up to this point. I think the original one is coming in at this point. It comes to here, and in this frame, this one decides to change direction and do a 180-degree orbit around this. And it's very interesting to me that it is precisely 180 degree, because it looks like when we had in Henk's experiment where we had the tungsten coil and you have a ball lightning and it goes round and it's over here, and another one merges on the other side 180 degrees. It looks like this. And I imagine that is like the Monopoles form by that 2007 paper. I can't remember his name. No, I can't remember it right now, but you can go into my previous work, where you get electrons that they're out of phase with each other, out of coherence with each other, but they're pulled to be in phase, and then they spiral down to the magnetic core of the pseudo-magnetic monopole. And so I imagine that this is just an expression of this overall behavior that is going on here, with this going around 180 degrees, which is akin, as I said, to the observation we saw when in what I call the tungsten chop shop. And so it gets to this point, and it's a shame we can't see the kink, but between these two frames, it immediately starts following, but almost in the reverse orbit around the original trace. But it's behind it. So the original one has come to here, and then it's over here, and then it goes from there, and it comes around and starts orbiting around it. This particular sequence of images, for me, is just completely earth-shattering. There's no other way to describe it. And this is what I really wanted to get across to the guys at Assisi. And I know you guys have seen it before, but when you first start seeing these things, and I imagine for most of humanity, when you see these sparks, You just think they're sparks. They're like hot things that are following kinetic trajectories. This particular video absolutely blows that concept apart. These things are interacting extremely fastly, and they are sharing information between themselves at a distance. At a distance. And that for me is just mind-boggling and wonderful at the same time. So we've talked about these before and how this is like this track. So essentially, for most of the research experience of people in the LENR, certainly since 1992, the first LENR sketch, in my view, in Solin's patent, although he ascribes it as a shockwave rather than an actual sort of track from a particle or cluster of something. But anyway, the point is that this structure here looks remarkably like one of these tracks, but just squished in a plane. And it might be that in the air it travels with this frequency, and in this particular material, whatever it is, it travels with a slightly different frequency. Anyway, so there we go. And here is a frame showing these tracks coming out. And that is the video. And we've shown this a number of times. And this for me is was also a particular moment because I'd seen these kind of things before. And the video is here. That's it. It's done. Because I'd seen this kind of track here in Baronoff's work. And again, this is where there's no magnetic field. This is not an explosive discharge. This is something that's living in the material that was exposed. This is this bismuth salts on a gold with gold foil on a silicon dioxide basically platter. And it has this track, which I believe is the same as this kind of track. Okay, so and there's the GIF anim of this particular pulse coming down. Okay, and then there's a whole other bunch of pulses, and I described how you know there's this another one of these bouncing tracks here, and the squiggles like the ball lightning, and then this one's quite nice because it's straight and then it goes into a squiggle, so that shows how things can change my directions. Now at this point, I'm going to change tacks here. Because what we're looking at in this next frame is a combination of 3 different experiments, and I have dealt with 2 of them in detail, but I want to talk about what I found in the first microscope session using the copper tube that Henk shared and sent over most recently, because this for me was like, holy moly, I know what I'm looking at here, I think, and I've seen this before, and this is something that needs to be communicated to the community because, frankly, the observations of weird sickness and damage at a distance and cancers and so forth really are explained by this. Now, I would like and advise people to go and look at the Shishkin presentation that I translated and gave a review of called A New Type of Penetrating Radiation. And this was conducted at Dubna in Science City and at his own private lab over a course of 9 years. And they found that strange radiation, particularly in the form of these birdies, these monopoles, that I believe they are and that they would argue are the same, they are able to capture ions of material, and they are able to transport them. And I described in the first part of my presentation in Assisi how in the titanium in the Amasa gas plus titanium versus PTFE, which is carbon and fluorine polymer, I showed that in the titanium there were explosively produced microcrystals with voids from the quantum coherent condensate, matching exactly the description of Solin in his 1992 patent. And that on these crystals there were regularly organized structures as described in Serlin's patent. By the way, this Serlin's patent came after publishing that work, but I'm just correlating the two. And that there were cones and rods, and that these were of material, and that the cones typically contained material that were alpha conjugate nuclei of titanium, and that the rods that came out were basically pure carbon. Now, Serlin didn't observe this cone and rod of different material, or certainly he may have done, but he didn't describe it. And to be fair to him, in 1992, the equipment wasn't as good as we had used at Alan Goldwater's Magic Sound Lab, and it wasn't as good when we verified it at Madison, Wisconsin University. But the cone is where you get the transmuted element. So this is the titanium with 3, 2, or 1 alpha particles from the carbon that was captured, I believe, from the PTFE, or synthesized from the collapse of matter from the titanium, regardless. And at the end of that, you get this nanotube of carbon coming out. And so basically it dumped its titanium with an intensity of alpha particles, i.e., I've described this with cold neutrinos. So like when the sun in the summer, when the Earth is closer to the sun, the density of the cold neutrino condensate is higher because of gravity, and that is why Alexander Parkhomov's beta detections from inverse beta at maximum energy of the beta decay go up. There's more detections, and that's because the Earth is physically going into a denser flux of the coherent condensate. And you can see this on like images of Bose-Einstein condensates, where you have a lot in the middle and out to the outside, but they've all lost their identity. They're all one quantum macro object, but it's like some are more equal than others, if you know what I mean. It's a bit funny to say that. So what I'm saying is that when there's an intense amount of material, you're getting the nickel. When there's less, you're getting the iron. Then there's less, you're getting the chromium. And when there's less, you're just dumping the last of the titanium atoms, where there isn't enough intensity to lay down those triple alpha, those carbon atoms. And then it just lays out the remainder of its payload of carbon atoms and produces this tube. And then conversely, on the PTFE itself, it's a little bit more of a mixed bag, because the PTFE is not a magnetic thing. It consumes the carbon and the fluorine ions, and they are inside the EVO, and then it's taking the fluorine and it's producing the sodium-23 and the aluminium-27 and so on, these alpha conjugate nuclei, starting with fluorine-19 as the base. But it's all kind of mixed up because there's less opportunity for it to produce ordered structures, because firstly it's a big plasmoid and you can see this burrowing into the PTFE. And also there isn't the opportunity to set up eddy currents and magnetic structures, because titanium is paramagnetic as far as I understand it, and so there's less opportunity for it to be so ordered. So I think if people go on with the experiments in this field, they are going to want to use materials that will allow them to study the aftermath. But anyway, that being said, talking about aftermath, this structure here, we are going to look at where I found it, why it's interesting that I found it there, and the other materials surrounding it. But before that, I want to help you understand what is going on at the macro level in ball lightning. And the way I'm going to do that is I'm going to return to a couple of videos that I referred to in Assisi, because that was my intention to walk them through this process as well. And then I'm going to show you what things are doing on the micro level. So bear with me, and I'm going to pull up some other material. If you've got any questions, now would be a good time to do it. Is the nanotube carbon diamond then? I know. I think it's carbon. I think it's a carbon, like a carbon nanotube. That's kind of the layer, the structure there. We've seen a amorphous diamond formed in the core of the Lion reactor, and we've seen how should we put this? Kind of fluidized diamonds and carbon sheets. So the carbon sheets could be graphene, and as I said, that this technology tends to produce all of the allotropes of carbon, and including buckyball type structures. And on that note, I think probably I need to show this image again. So I'm going to show this image again. So this is the Bogdanovich et al. 2019 paper, I believe it is. Yeah, 2019. I think it's from May 2019, where he recorded these plasmoids moving around on his metal 2 days after the plasma flow discharge. And he also recorded on video these crystalline structures, and you have these toroidal structures or other structures there, with some sort of thing joining them all up. Now you can imagine when you saw these things traveling in the traces that I showed you, and you have one track and there's another track, and they kind of like are kind of connected to each other, that kind of connection is the same kind of connection you're seeing going on here potentially, and that maybe they can all coalesce and group together by using this same kind of whatever it is that's connecting them. So I think I'm going to look at some of the old videos, and they're not that old, but old to some of you guys because you've seen them before. Let me just find that in here. Jason Cook, at the presentation, do you feel that you won them over? Certainly. I asked them if they had another explanation for what they're observing, and they couldn't really practically come up with an explanation. That's why I had to take the presentation so far. Otherwise, you know, you don't have anything that leads them with some thinking. But also there was a lot of interest in having copies of the presentation and to review later by, for instance, Jacques Rau, the head of the French Cold Nuclear Reaction Society, and I know the Russians are chomping at the bit to get their hands on the data for the coherent matter traveling waves, and I was contacted by some long-term LENR researchers in China this morning, and they wanted copies of the slides as well. I think if Western people sleep on this, they're going to completely drop the ball. They're going to completely drop the ball. I was also contacted again by Michael Claridge of the Sapphire Project as well, and he had the same question, you know, kind of like, are you waking them up yet? And I think really there was a sea change. There were some comments made outside of the presentation where it was essentially said that I think we can see that this is probably how it works, and we need to kind of think about it. So for those people that witnessed it, there are still massive vested interests, and there is this belief that things are only possible in the way that they've always thought that it's only possible. But for me, the journey has been interesting because I've observed these things. I've said, this looks like this, and I think this is what's happening. And then I've been resoundingly mocked by even people that I knew very well in the community. And then I've later found that other people have had these things put in awarded patents, some of which, like the Lockheed Martin patent, are absolutely current. And so if the world's greatest defense contractor and you know, the top the Russian research community, both in the Soviet era and since, they believe it's ball lightning. That is the way this works. And if you have the US Air Force saying in fusion technology that basically if we can master this, we can master fusion at almost any scale, and it's self-confining, then it's kind of like, you know, and you observe the same transmutations where you physically can see the ball lightning, and then after it's happened, you can see the same transmutations you see in LENR. Then for me, it's kind of basically it's done. That is how it works. And I think by the end of this presentation, when you see that what Dave and Henk have produced on the macro level, and you can see that working on the micro level as I hypothesized, but I've seen a lot of data, so and studied a lot about ball lightning. When you see it on the micro level, even with the data I've got now, I'm pretty confident that when I dig in a little bit more in the next microscope session, which is in about 2 weeks' time or a week and a half's time, I think we're going to absolutely nail this. And I think if the scientific community that are pretending they're going to do fusion don't catch on to this, it's going to be a disaster. It's going to be a complete waste. I mean, it's one thing to waste money when you think you're doing the right thing. It's a completely different thing to waste money when you know in your heart of heart you're wasting your life and other people's money. That is a crime in my view. So yeah, it's all coming down. I mean, this is not done by no one. This is done by the nuclear research community in the National Research Nuclear University, Bogdanovich. Those tracks that I was showing you earlier from Klimov were being done by the All Plasma Physics Institute of Russia. So, you know, and China are not going to sit by and wait on this. And I can tell you Japan have been researching this. And we know because of the US's interest in anyone who knew anything about ball lightning in October 2001 and related technologies, we know from that very report that they were researching this in 1950s and 1960s. This is not a new thing. It's not a new expectation, and I think it's going to become clearer and clearer until it's basically you cannot really think of it in another way, in my view anyway. So I think we're going to go back to a couple of the early Vega videos, because I think they get across some points that I think are very important to make clear. Just bear with me. Okay, we want that one. Okay, I think the first thing I just want to bring up again is this slide by Georgy Mesias of the ecton emission sites. Now, the explosive electron emission is effectively like a Coulombic explosion, rather. And this work was published first time in the West, I think in 1996, but he'd been working on this since the 1970s. And I think what we're going to... I've already explained the working of the Parkhomov 225-day reactor on the basis of micro protrusions. And this is what Shalani is doing, as well as oxides, and this is what the Conrad is doing with the EU group. And microparticles and so forth are what Mizuno was doing in his previous, other than the R20 reactor, he was doing that. But we're going to be looking at these grain boundaries emerged at the surface. We're going to be looking at this in the copper tubes of Henk. And it's just beautiful, and effectively it's similar in some respect to cracks, but this crack image here also has adsorbed gas layers on it, so there's a combination of two things going on here. Okay, so you'll recognize these from Henk's Vega videos, and there's pimples popping in and out of view here. But in this one particular image, you are seeing the self-organized what they call balls of fire in the 2001 fusion technology paper. And then you see some of them that are wetted together, like these three. And then when there's more of them, they kind of start to wet together into a more homogeneous kind of layer until they get up to a point where they're all effectively one layer. And then they can get double layers and they spin round. So you can imagine that maybe there's some spinning going on within these things, but you don't really see it. But here, it kind of all merges into one. So if something was going to build on the micro level, I would have assumed that it would do kind of the same thing. And, you know, we've observed that these things can cut holes into things, most recently in the copper pipe. But this has also been observed with the 10 yen coin in the Amasa gas in the past. And so here's another Henk video. And it's very noisy because of the fans in the background. But again, when you look at this from the far view, it just looks like one big glowing ball. But when you zoom in, you can see that it has some structure and there's some double layers here. And you can kind of see the shadows of where the balls of fire are kind of underneath, and they're a little bit more energized than everything else. But other than that, ultimately, this will end up as one smooth structure around it if you keep feeding it. And this one's quite nice because it shows a little bit of the self-organization. So if I pause that there, you can see... here we go. There we go. So you can see these balls around here. So what I'm showing you here is that almost without concern for the geometry, there will always be some form of self-organization going on. It will take the opportunity to start building these structures. So in this one, we showed that this is what most people have seen in their sort of experiments, is this hemisphere here that ball lightning tends to produce, or these self-organized plasmoids like to produce on a flat surface. And that will be important. But given the right environment, they will tend to produce a circle here. Okay, and I argued that you can see that this part of this nickel foil is poking out, but it's only poking out as far as the end of the outside of the double layer. So there is something special about this that allows it to orient in the way that it does. And I looked at this Popescu and Lozneno paper from Journal of Plasma Fusion Research from 2001. And their view was that the ball of fire was essentially, this is a top view with the charge distribution, and this was the side view, and this here was the kind of change between the positive inside and the negative outside. And I have said that if you just look at this model alone and you've got more matter coming in and more electrons, you have a scenario where you are at this point here, which is the inside of the double layer, you have less and less and less degrees of freedom. And so if there's more material going in, then you're going to get to the point of coherence, because there's no degrees of freedom left on the inside of that double layer. And I believe that that is why you get these very, very extreme changes when the coherence reaches a certain point. Now, there was a slide that I shared from a Russian presentation, which I'm going to share here now. And this is showing how organization of charged plasmoids occurs. And again, you have these shells, these double layers, and the plus sort of core, and they can arrange themselves and group together. So it's kind of like. Interestingly enough, I've been talking, as I said, about these things having allotropes of carbon as their structure. And when I saw this presentation, it's like, well, the Russians already know this. And they've literally got a buckyball here. And they've got something penetrating inside it. So I think this is interesting. And when we talk about the Vega Valley, I think it's going to become very clear what's going on. But I'm going to briefly discuss some aspects of the Vega Valley today, which is key to another feature that needs to be made clear. And he's got this kind of standing wave going on here with this central point, and he's saying, you get this energy maxima here, blah, blah, blah. Anyway. So just to drum home the point here, this is a steel coil, again from Henk, and this GIF animation shows very, very clearly how quickly these balls can wet together. And in fact, the Popescu and Lozneanu paper does actually discuss how these potentially are wetting together. But this is, in my view, one of the clearest videos that shows this process happening almost instantaneously. And this is important when you're imagining how it's eating the material at the micro level. And in this, I've just played with the contrast. And the reason I've done that is to highlight this sort of fuzzy nature and the kind of scale of this outer double layer, that there is this hard area. And like I said at the top, this here is the double layer, which you can see around the outside here. But the nickel is only going sort of between here and here. And I think you're going to find that this double layer and the way it influences matter is extremely important to what the structures that you see in the Vega Valley, and also the structures that you're going to see in the copper pipe, which I'm going to show you. And I'm just totally stoked to be in a position to be able to show you. So I have to thank Henk, and I have to thank the team at C.I.C for working with me on the analysis. And here you can see how fast these things are forming, and it's like literally forming this skin in 1/30th of a second, and it's probably forming it a lot faster. You can't see it, but anyway. So I think these are very, very good context images for sharing at this point. And I think there's one other image I want to find because, as if I can find it. Where is it? I might have to go to YouTube. Oh dear. Okay, here we go. Talk amongst yourselves. There you go. Okay. So, the video I want to refer to here, and I don't want any nonsense coming with an advert, so we'll get through this. Okay, so the video I'm referring to is this one. And Henk might have drilled some holes in here, but it doesn't matter. My point being is that on this spherical surface, he's created some virtual faces on which the balls of plasma, the fireballs as they call them, these tufts as the Sapphire group like to call them, they are forming in a regular array around this ball, and when the power is turned up, they start to wet together and form something that's going around. More of this, and essentially he's turning the power up and down in this. So when there's more glowing action, it's more power, and when there's less and so forth, there is less power being applied. Now what I'm going to show you in a minute is some 8K images that I made in the SEM, and these 8K images are showing in my view exactly what's going on. So if you recall, what I've been saying for quite a while is that you have a nucleation point, and the ball lightning grows and it eats some material, and then it collapses that material down into a shell, and then the process repeats. That is my hypothesis, and I have argued that the material from John Hutchison was a good indicator of that occurring. And I have some, where is it? Some material examples. Somewhere here of John's material. Okay. But I think the key moment for me was reading in late October 2018 this paper by Microscopic Observations of Palladium Used for Cold Fusion, and there is links that you can find from things that I have shared in the past. That's going to show it there. Microscopic Observations of Palladium. And so there was a palladium electrode here, and he did it in deuterium and an electrolyte, I think. And you have when he cut it open, he found these holes inside. And when you go in and look at these holes, it's not just that they are cracks that formed in there. It's I don't know if you can see that, but down there are these round areas that got eaten out between the crystal grain boundaries. Remember what I was saying? That was given by Messias. He said that, crystal grain boundaries, okay? And then he goes on and describes how these get bigger and bigger, and you can see that there's these round structures, and I've shared these kind of features on the surface of the ball burn samples. You can see it eating around the material around the crystal grain structures until it basically eats a whole crystal grain, and around that crystal grain you get elements formed. So in this paper he describes the process like starts with a crystal grain, little balls form, and then it kind of goes around the crystal and eats more of it, and then it goes around until the grain is eaten. Okay, and then in a subsequent paper I think also, so that one was a paper published in Fusion Technology and it was received by Fusion Technology September the 21st, 1990, 31 years ago, nearly. And this one was received March 19th, 1991. And in here, again, it's a classic kind of cold fusion apparatus. You've got I think it's a platinum wire, a palladium rod, and so forth, heavy water with 3% sodium chloride. And in there, he found these areas eaten away, and they had elements around them. And given it's palladium and deuterium, guess what? You've got sodium, magnesium, aluminium, silicon, sulfur, calcium, and copper. And over here we've got titanium and iron also synthesized, and so forth. So these are the kind of things you expect from this reaction, and there they are all the way back in 30 years ago. And so how is this occurring? Can we see anything similar? So I took the copper pipe, and let me just see if I can find an image of what the copper pipe looked like, and then we will look for the SEMs. So bear with me. Again, I must thank the research community, the experimentalists, for working with me on this, the analysis team, the donors out there through the years, because this just simply would not have been possible. It's such an honor to be able to share these things with you. So thank you, Dave. Thank you, Henk. Thank you, Charles. Thank you, John. Thank you, so many people. It's, I could do that all night. Right. I'm going to have to think and not just click now. This is where I'm going to get a little bit more disorganized. So sorry about that. Okay, so the first of these videos, which, oh no, I've just copied it to my desktop. I didn't want to do that. So the first of these videos, so this shows you kind of the orientation of things. So we're looking from the top of the chamber down. This is the anode sort of sheath, which is giving some insulation to the anode. The anode is on the end here, and this is a big iron block. Now we use iron because it is magnetic and it will allow collection of monopoles, and there's a big iron block below. Now the reason there's copper in there, and there are actually zinc sheets under here, so maybe I can dig out the images for those. So the zinc sheets, the zinc is used because it's both pyroelectric and piezoelectric. That's zinc oxide. And so the idea is that that would stimulate the production of exotic vacuum objects. And the copper here has copper oxide, which is photoelectric, and that's why I asked for copper to be put in there. And so this should cause promotion of exotic vacuum objects. When you've already got them formed and they're shedding these high energy X-rays, they should promote the production of more electrons and feed back on themselves. And so they are, Henk, that's why I asked you to do that. And the tubes are self-reinforcing. Now the interesting thing is it appears that the zinc has disappeared, and actually I can't recall immediately, but we're going to look in a minute. I don't actually think we see much zinc in the analysis. I think it's just gone. There seems to be some phosphorus synthesized. However, phosphorus is used to deoxidize copper pipes, so it might have just been in there at a level, but maybe it provided a target nuclei to synthesize more to. But because it was there already, we can't really conclusively say that that is what's gone on. And the middle pipe appears to have disappeared. Anyway, I'm going to pull out some other images so that you can see what was going on here. Just give me a look at that for a second. No, not that one. Ay, ay, ay. So this one's quite interesting from the point of view that it shows how the metal can appear to get very hot very quickly. So we'll just play this. So you've got the discharge going on there, but if we zoom in, you can see that the copper is not melting, but you see you've got a ball of fire under there, but it kind of like goes extremely, hot looking, goes yellow or white hot. You do have to bear in mind that the cameras are sometimes oversensitive to what do you call it, infrared and stuff. So if you move on, you can see here. Anyway, the point is that the radius of these copper pipes generally maintained its its radius. It didn't kind of like melt and flop down. But the other thing is you've got these, the iron itself here seems to like switch between temperatures. You can see some balls on the anode there in the foreground. So you can see the ball forming there. So he added hydrogen. Yes, I'm talking about the photoelectric effect. So I've kind of given a little bit of the game away on something electric part 2, but it's going to get a lot more exciting. I'm it's difficult to know which exciting thing to talk about first. There's so much of it. Right, so let me see if I can find the actual teardown, which I have here somewhere. Thank you to Henk. So this is the teardown, so you can give see the kind of scale of the materials involved. And he takes off the top here. So you can see the kind of arrangement here. Now, what we are going to look at actually in, if I could move this out of the way, which it doesn't appear that I can, that's annoying. Why would you do that to a controller? What we're going to look at actually is this ball. We're going to look at a little bit on this ball here. And there's a little tip here. And we're going to look at that in the SEM. But the thing to note here is this yellow, orangey yellow thing that seems to be deposited everywhere here. But also these kind of balls that you're seeing cut out from here, and these circular sections that are cut out, and I will look at these with a little bit more detail. I think it's in this video. And actually Henk's done a very good job. He's getting very good at, you're getting very good at the camera work here, Henk. So you can see the scale there, and this is around about 10 millimeters, and this is the exact scale of ball lightning that is referred to in that 1993 submitted US Air Force working document that was published in Fusion Technology in later in May 1995, I think it was, or whatever. But anyway, the point is that they are describing that if we can generate balls of fire of the sort of 10 millimeter variety, we could produce fusion reactors, and that would be good. And there we go. Oh, sorry, where did that go? Let's go back there. So again, what you are seeing here is something akin to what was observed with the 10 yen coin, with the real-time kind of production of the plasmoid in the Amasa gas exposure. Very, very sharp line, very sharp line. And for those that don't know, copper is one of the most thermally conductive materials. And not only that, it's sitting on a large lump of iron. So you would have expected, if it was enough to basically remove completely this material, that it would also be hot enough to kind of melt. And if you can look at these microscopy images that he's done here, it's very, very sharp, this line. It's very sharp, just as he observed on the 10 yen coin. And here's another one. So what we're actually going to look at is this tip. Maybe I can find a better frame where he's more in focus. In a second. You see how yellowy orange that is? Well, that'll make sense when we look at the analysis. Now he turns it round in a minute, if I can get there. Okay, you can see how sharp that point is. And that is the point that we're going to be looking at under the SEM. So it's a very small amount of material that we're going to be looking at. I think he's got it, maybe it's in this video. Yeah, maybe it's this video. No, it's not that video. Which video did you do it in, Hank? Not that one. It's probably this one. Okay. No, it's not that one. Oh well. It's one of these videos. Maybe it's this one. Yeah, it's this one. So you can see here, what you're looking at here is the ball. There was an iron plate. Okay, if I go back. There's an iron plate that this is sitting on, an iron plate. And the ball is formed on the iron plate, and it's cut this circle out of this copper tube. And then as we go and Henk rotates it here, he rotates it there. Okay, so that's rotated roughly through 90 degrees. You can see the half ball of the plasmoid that was on the iron plate. So it's cut a radius out that way, and it's cut a radius out this way, which is quite impressive. It's a 2-aspect radius that is cut out here in this particular piece of material. And so that's why I found this particularly interesting, and we've cut this out and put that under the SEM. Okay. So, let's have a look at the SEMs, shall we? Oh, love it. Oh dear. Is there anything else I want to do before we go there? Okay. Right. CU pipe Vega Valley. Just closing a few applications so that my machine doesn't fall over. Give me a sec. Okay, so I like this shot because it shows the main structure that is on the surface of these, the inside of the copper. And essentially you've got a skin, and from the skin there are growing these nanometric wires. And interestingly, they seem to have these loops at the top, you see? We've got these loops. It almost looks like a deep pile carpet. And I like this shot because we are looking top down on the structures with a slight angle. And we've got a piece that's broken off, and we can see side on. So we can get an idea of the scale. So maybe if I come out of this, it's going to stop showing that message. So we can see that this is 5 micron full scale. So it's almost like that this is 5 micron. This whole thing here is about 5 micron, which is interesting because this is the kind of scale of an exotic vacuum object. Whether that's relevant, I don't know. But let's go and have a look at the material that we are looking at here. So I'm going to go and get the analysis, which is in... So this isn't prepared in the way that maybe it would have been nice to prepare, but all the same, I think we'll be able to tell the story. Okay. Somewhere, oh, there we go, Excel. I can't work out whether my machine's stopped or no. Okay, it's getting there. I'm opening a Microsoft application. Ah! No, please, no. Oh dear. I could literally draw this with a pencil faster. Okay, I'm going to actually quit Keynote because it uses a few gig. Because we're just going to be looking at the images for now. Oh dear. I think when I get my next Mac, I'm going to get it with 32 gigs of RAM. Gone are the days when 16 is enough for me. Okay, all right, come on. Okay, all right, that helps. Okay, is it going to allow me to put an image up as well? Okay, maybe not. Dear. Bear with me. Sorry. Oh no. You can't possibly be this slow. Okay, I'm going to quit a few more applications. This is going to be really worth the wait. It's going to be really worth the wait. Sorry you're having to wait, but you've only been waiting for like ever, so it's not that bad, I guess. Hopefully. You know it's bad when it takes you 3 minutes to close down an application. Come on, I've just, all I've done is open Excel. It's not that bad, honestly. This is when I need some hold music. I should have a video prepared where it's just like elevator music. I'll read your questions because I can see if it's doing something useful in the background. How about that? Okay. All right. Okay. I've nearly got some joy. It's still closing down an application. Okay. Is it going to allow me to do that and that? Can I do that? Is it going to allow me to do that? Does it see that as a different screen? Ron, you do know you can run email and eBay on a phone. Okay, all right. We are making progress, I promise. Come on. I've nearly only got one application open now, and that's Excel. I can't believe that has crippled the machine. I might have to go to OpenOffice. Okay, I'm bored with that. I'm now going to force quit Safari. Sorry, this is very tedious. Go and have a tea break. Safari not responding. Yeah, I know. Thanks for letting me know. Okay. Safari is a resource hog when you've got about 100 tabs open, which is more my problem. Right, die. Force quit. Right, things should run more smoothly when it gives back that memory. I never understand when it says 940% CPU. I'm thinking, did I get 10 more CPUs? Right, okay. Okay. Nearly there. Nearly there, honest. God. Just waiting for the CPU to cool down. Okay. This is exceptionally tedious. It's well worth it. Thanks for sticking with me, but you're not going to regret it, honestly. You're not going to regret it. I don't want to have an office update in the middle of my presentation, thank you, Microsoft. Just go away. Oh, dear. Are we having fun yet? Right, okay. Oh, that was hard. Right, good. Okay, we'll put that over there. We'll put this over there. Right. Still running like a dog. Sometimes I think Microsoft build their applications out of Lego bricks. Actually, no, it probably worked better then. Okay, all right, I think we got it there. Ta-da! This is all I wanted. One image window and Microsoft Excel, that's it. with a few tables in it. Anyway, so what have we got? So Spectrum 1 here, which is kind of this area on the end here. This is 1.8%, 1.9% carbon, 25%, or 25.5% oxygen, and roughly 73% copper. So this is essentially copper oxide, cuprous oxide. Is it cuprous oxide or well, it's mostly copper. This is mostly copper. This amorphous blob here, you see here, this is amorphous, and it's mostly copper with a little bit of oxide and a little bit of carbon. Now Spectrum 2 is looking at some of the tip area here, and Spectrum 2 doesn't really show a lot of difference. Ignore the nitrogen, it was just requested to be there. So yeah, it's essentially the same even on the end of this. And then looking at the end on, which is somewhere down here, Spectrum 3 is mostly copper. So the very tip is mostly copper, it would appear. So we're looking at, oh no, actually, I don't think we're looking at a copper. Why did I look at that? We are looking at what might be an Evo. We might be looking at an Evo that's trapped in the top of these copper fronds, and that's what I've looked at in this image here. I've forgotten I looked at it like that, and that is almost entirely copper. Very much more so. Well, not really. What am I looking at? 74%. Oh no, what I'm talking about. It's exactly the same thing. So whatever. This tip here is the same as where are we? It's still going like a dog. No offense to dogs. Okay, so we're looking at the end here, and this is 74%, 72%. So they're all pretty much the same in this shot. So this, unfortunately, is the tedious shot of the shots. But I want to show you one shot on this, which is this one. When it shows you. This, in my view, is an exotic vacuum object that is 50% into the surface that I just showed you, which is, as we said, about 5 micron deep. So this is the carpet layer of copper oxide that we've looked at. And this exotic vacuum object with our D, 2, 3, 4, D4D ratio has crash landed in planet fuzzy copper oxide land. Yeah? And so what is this composed of? Well, we will find out. Let's find that thing. You cannot be serious. I'm just changing tab. It's just changing tab. Right. So let's have a look at what our EVO is. We have a spot on this structure here, which, I don't know, it might just be a piece of detritus, but it's, you know, it's there. So we look at that in spectrum 12. Spectrum 12 is, by percentage atomic mass, is 22.7% carbon atoms. Its oxygen is 50.56. It is 9.6% potassium, 1.98% iron, and a little bit of copper, 15.17 copper. But by weight, it is still 38% copper. So it's come from the same family, but it's a nice little crystal. Now, looking at spectrum 13, which is on this ridge of our EVO strike here, the ridge there is 10% carbon, 45.5% oxygen, potassium is 1%, but 28.51% iron. 28.51% iron and 11.48% copper. So I'm going to zoom in so you can actually see what I'm talking about. So in the center over here, where I'm pointing my mouse on the left, we have 28.51. By mass, that means it's 50%, 48, nearly 49% of this EVO is iron. And this is wonderful because it's an iron cored exotic vacuum object that's landed 50% into this material. And as you can see, the D on this is what? It's I guess it's about 4 to 5 microns, the D. So this is a 10 something micron across 15 or something, somewhere between 10 and 15 across. It looks like 4 actually, so it might be 16 across and 4, which is interesting because if you recall, in the Hutchison fracture sample, we had a 400 micron D and a 1600 micron 4D radius exotic vacuum object. That was the largest one we observed. So this is a couple of orders of magnitude smaller than that. Is that right? Yeah, about that. So 4 microns compared to 4 to 40, 400. That's 2 orders of magnitude. Yeah, difference. Oh, hopefully I've got that right. This is largely iron. So I really like this surface as a landing zone. And again, it's about 50% sunk in. And this is what we see with exotic vacuum objects. So there's that. Now, what I did actually was I did a couple of line scans. And what do I mean by a line scan? I mean, if I can zoom in with this without it crippling itself, I've drawn a line from the inside to the outside. So from the inside of here, about here, to the outside over here. And you can see, looking at the iron, that as you go over the EVO structure, the iron goes up, and as you come off it, it goes down. And there we go. That's the line going across the material. And so there's the line. And I did it again. I wasn't happy doing it once. So I did a line from here down to here. You can see on the original image up here down to here. And you can see it's nothing in the center, and then suddenly it goes... sorry, this is copper. There's nothing in the center here, but as soon as you get to the outside, it immediately goes up There we go. So just on the outside, a little bit beyond the outside actually, and I think that's important. It immediately shoots up with the copper, and we can see that the iron and the oxygen here. So that's yeah, iron and oxygen, because we know these things like to make magnetite structures. The iron and the oxygen is where the EVO ring is, and the copper is outside of that. So there we go. This is very nicely showing that this is an iron cored exotic vacuum object that lay on this structure. And I'm very keen to have a look at this in other examples. I talked about this structure, and I'm going to do separate videos on this. But there were two what I call pretzels. There was this one, which is the classic kind of pretzel. So this is the, in fact, this is, if you look, this is where the Evo strike hit. So you can see this is all copper oxide. In fact, let's find out where that is. You might as well do it here. Not there. No, we're not looking at that yet. Oh, well, anyway, this is the copper oxide. That's our iron Evo that hit it. And this is carbon rich in our magnetohydrodynamic structure. And I believe that this structure is responsible for building this lead structure up. And there is a similar one over here. But this is much more interesting. Like I say, I'll do a separate video on this because I want to do more analysis on this. But you've got carbon and silicon and types of things here. You've got your Matsumoto sort of tube, which is carbon. And down here, if you go in close, you will see that this is calcium. So we've actually got some twisted calcium structures here. And over here, you've got these like a braided tube. This is almost like an exotic vacuum object. And that might be giving you a hint about where I'm going. But you can see you've got these segments of stuff that I believe was in the magnetic flux loop that was between the left and right side of this pretzel, as I call them, or it's the yin-yang pair. These are like effectively a magnetic loop goes between this and that. You might like to think that as a north and south. Anyway, so what am I looking at here is I'm looking at structures on the copper, and I actually have an 8,000 pixel image here, and we're going to have a look around this because it's really rather beautiful. And I think I'm going to look at this with a different viewer so it doesn't give me that naff thing down the bottom right. So come on, give me a preview. Okay, so in this one I can zoom in without it causing me too much problems. Okay, so is everyone with me? Right. Now this actually is that little tip of that copper pipe inside. And what you're going to see here is exactly what Matsumoto observed. And you are going to see grain boundaries over here, for instance, grain boundaries that have been eaten away. Okay, you've got these little round holes and areas eaten away in the grain boundaries. These are like almost dead ringers for what Matsumoto observed. You can go over here as well, grain boundaries. Okay, grain boundaries with the little holes in them and so forth. But the thing that you might have also already caught on, there are more interesting structures like this. These are regular areas, and I would suggest that to you that these are inclusions. So we've done the grain boundaries that Messiat suggested and that was observed by Matsumoto and published in 1991. And these are the, I would believe, inclusions, or they are the points where the self-organized plasma has located itself. Okay? And you can see they are all over this sample. But that, for me, is not the really interesting thing about what you're seeing here. And I'm going to get better and better images of this. But this, for me, is absolutely boom. Wait for it. First up, I'm going to bring up 3 images here. Okay. Okay, let me do it like this. Okay. So this is the overall image, okay, and it almost looks like these self-organized structures are have a cap on them, and there's a hole in every one, and that they appear to be blowing material through the crust that's above, and we already know that this crust is copper oxide. So it might be, to a degree, vaporizing copper oxide and spraying it out. Okay? All right? This is not what I would call normal thermal melting. It's something else is going on. Now, look at this next image. This is a close-up on one of these structures. And guess what? This is 5 microns. Each of these divisions is 0.5 of a micron. So this shell here is about between 0.5 and 1 micron. This is what was observed by Anatoly Klimov. And he told me in Sochi in 2018. I get these spheres in my inflow plasma Tesla shoulder-zified energy generator, and I get all these spheres formed, but they're hollow, and their shells are about a micron thick, and I don't know what they are. Well, I think they are the double layer. You're seeing the double layer here. But over here you can see an example. Where is it? Here. If I go back. Here's one that's like a much younger one. Okay? Over on the right here. And it's still keeping this thickness. Now, what you can imagine is that some inclusion or whatever has initiated, and it's produced a ball lightning, and it's eaten a bit of the copper, and then this collapses, or the material gets ejected, and it gets bigger, and so forth. And you can see a couple of them here, yeah, around here. And here's some others here, okay? And let's go and have a look at what they are under the EDS. Let's have a look at what they are. I can find them. Not there. Somewhere. Okay. So I've got Spectrum 8 and Spectrum 7 are looking at the 1 micron or 0.5 to 1 micron shell of this thing. And Spectrum 7 is 2.75 atomic percent carbon. Oxygen is 29.79 and copper is 67. Okay. Spectrum 8 is 3.12. Okay. Now, Spectrum 9, which is the surface, that is 0.5. Okay, so it would appear there is approximately, if you take the average between these two, there is a 6 times increase in concentration of carbon in this shell here. Okay, and there is what, any increase in oxygen? Yeah, so the average kind of between these two on the oxygen is 30%, and the oxygen on the outside here is about 23%. So there's an increase in oxygen, it would appear, and there is a 6 times increase in the amount of carbon. Okay, let's go back to it. Now, the next thing I want to draw your attention to in these structures is something that I can only reveal by taking it into Photoshop. But before I do that, I've got to show you something in Keynote again. And it might then become clear why I kept pointing something out in my presentations that we would probably come back to. So what I'm referring to is this. And I'm referring to these itonic meshes, these kind of buckyball type structures, but they're not quite. They're kind of these meshes that form. This is in Matsumoto's and this is in the Amasa vibrator plate. Okay. And notice that there is a gap between the outside of the itonic mesh, if that's what it is, and the outside of the overall structure. Okay. All right. Now, I'm going to load Photoshop, but I'm going to get rid of that first. Maybe. I don't know. Let's see. Let's see if Photoshop will load without giving me grief. And I will load this image in. Not that image. Typical. This image. Okay, give me a sec. Now, I recommend that if you're taking SEMs, you always try and take them at 16-bit. And the reason I say that is because normally when you're doing SEMs, you use the auto contrast, and so you can kind of get a read on the structure that you're looking at. And but often, as with photography, there can be things hidden in the shadows, and there can be things hidden in the highlights. And in this case, I wanted to know what might be hidden in the shadows. So I will look at this one over here. I'm going to have a really good close look at it. And I'm saying, darn it, I can't see what's in the shadows. But by using the level tool here, we can have a look at what's in the shadows. Can you see a mesh in there? Is it like a hexagon here, and there's something going off here, and there's something going off here? Is this the remnants of the itonic mesh inside the ball? Is this the equivalent of what we are seeing here? The mesh inside the overall structure. Is that what we are seeing? Is there some type of mesh structure that underpins the inside of the double layer? Fascinating. Fascinating. Now, remember what I was showing you earlier? And I was showing you the way the plasma organizes itself into balls and then they wet into spheres. Well, firstly, before we get to that, you can see here that not only have we apparently or seemingly got a mesh on the inside, we also have geometric segments of the higher carbon and higher oxygen rich structures that are in this up to it's between 0.5 and 1 micron or 1.5 micron shell. I remember Solon is saying in his patent that it produces these shells, and inside the nuclear reactions occur. And we observed in Matsumoto in my previous presentation where something is happening in the inside, converting the lead to carbon, and the carbon spraying out. Okay, and I think Henk will confirm that he often sees a lot of carbon being produced, or it seems to be, because the the viewing window gets smogged up with something. Okay, so we're seeing some structure inside. There seems to be some geometry going on here. Is there anything else we should be interested in? Well, I think there is. And we'll have a look at this. And what is that? Well, if you look at this ball over here with this open hole on the top, you'll see that it has these faces, which I've kind of highlighted in other examples. But it's got these faces. And on the faces, there's what looks like a circular structure, and 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 a circular structure. Is what we're seeing here the ball then collapses, forms a geodesic structure, and then on the faces of the geodesic structure, like we saw it on the M10 nut, like we saw it on that sphere where the bits were cut out, you get the balls forming, and that they are eating the material around them in the hemisphere, exactly like we saw on the 10mm section cut out of this same copper tube, right? And if that then, they all mesh together, when their coherence and they get enough energy and they all join together, they end up chopping out another circular section. Are we seeing this process move forward? And as it goes forward, it then chops out more and collapses it down. I believe that is what we are seeing. I believe that's what we are seeing. So if I go back to the overall shot, we need to do more studies on this. For instance, this one's quite nice because it has a structure in the middle and there seems to be some structure around it with almost a bit of a spin. But if you go and look at any of these balls, they seem to have these hemispheres around their faceted surfaces. That one's moved a little bit, but like I say, here there's one here which actually this one doesn't even look like it's got the cap come off. But on the facet sides, you get the round balls around the outside. Here, look, you got one here, and then you got the material around the outside. I believe what we are showing in those early Vega videos on the macro scale, in the multiple millimeters to 10, 14 millimeter scale, with the multiple millimeter sized balls of fire, we are seeing here on a much smaller scale around these structures that are eating themselves into the here. Look, you can see the same thing going on here. You've got the facets with a ball around it, facet with a ball around it, here ball around it, ball around it. I think it works on every scale. It's the same on every scale. So this is a lower resolution of what we've just seen. It might actually be easier to see at that level. So we've got a section eaten out here, section eaten out here, and these are the segments. Okay. Now, is there any other evidence of this? Well, let's have a look. So the next up is this, and this is the ball with the little bit sticking off it. And we're going to look at this area here, over here. The reason is I saw two little balls and a hole. And in many samples, I've seen these spheres kind of like half in and half out of a surface. So this is a spherical ball lightning. This is a spherical EVO. And we saw over here the toroidal ball EVO. Ball EVO? The toroidal EVO here, which we zoomed in and looked at here. Okay, so now we're going to look at examples of so-called spherical exotic vacuum objects, and those are the two types identified by the US Air Force paper from 1993 by Matsumoto and by other authors as well. So these are the kind of structures that you will expect. So we are looking at this ball, but we're going to be looking at this area. So let's go and have a look at that area. So here is a close-up of this area. And let's have a look at this ball up here. Well, firstly, if you go into it, it looks like it's lost something up here. But it looks like it's more crystalline in nature. You've got these kind of like more kind of like buckyball type profiles on the outside. It's not what I would call a perfect sphere. Bearing in mind there's copper oxide grown on the outside of this as well, and that this might be more iron rich than the environment. And so this is something I need to confirm. But it certainly looks more faceted than perfect round that it appears at a distance. And so that is interesting. It's all in its own right, but it seems to be submerged. And look at the other one over here. Again, this has a lump on it. This is less kind of like faceted than the other one. And it's difficult to tell whether this is right in the surface. But the hole over here, let's have a look at the hole. The hole has a hexagonal kind of section to it. So it's like a ball lightning landed here. There's some other detritus from subsequent events, but it kind of embedded itself into the surface. And if we zoom into that a little bit more, because we can do that, because we've arranged it so that we can. Let me go here. It's going to let me do it. Okay, so we've gone in a little bit further, and we can see that is quite smooth in here. So it's almost like this is our carpet with our fluffy copper oxide type thing, and this is almost like the ball went in there and it kind of got stuck. But the fascinating thing is, I don't know whether it's very clear to you, and I will want to go in and look at this at higher definition, but there appears to be some structure in here, and I've kind of highlighted this section here in this image. If I didn't load it into Photoshop, that would be more helpful to me. No, it's loading into Photoshop because it's a Photoshop file. I've loaded it in here, and it's just a slightly contrast adjusted. Anyway, I believe that what I'm seeing here, but I need to confirm, in this area here is a repeating section. A repeating section. So I'm giving you the bleeding edge here. You know, I'm not absolutely certain here, but I believe that this is a repeating section. And I think that if you look at this, you've got a section coming up here, section coming up here, across there, up there, and there are other signs of it underneath this detritus. So I'd like to get in there and maybe look at other examples of this. But I believe that this may be the scar left by the itonic mesh when this EVO, this micro ball lightning collided with the copper oxide. But it was over to the left that I got really excited with this little beauty. Right? Now, what are the scale here? Well, this is about 50 microns. 50 microns. The balls are about 50 microns. That is the kind of scale that normal ball lightning is. One of the quanta of ball lightning. Not this because it's got copper oxide, but the actual hole that it's created, the sort of 50% in hole, where you haven't got the growth of the copper oxide in the same way. If you look at that, that is around about 50 microns, bang on. And over here, you've got something that's essentially around about 10 microns or so in its diameter. And do I have a closer shot? I might have a closer shot. Yes, I have a closer shot. Oh, I have a closer shot with some details in it. There we go. I've even got scales on here. So between these knobs, here, and there's one down here somewhere, the period between the repeat on the structure, it looks to be about 15 microns. The thickness of one of the bands in this overall structure, here, this thickness in this band here, is about 2 micron. And it all seems to be around about 2 micron. And the overall width of the structure is about 10 micron. And this is interesting for me because I've seen something similar before. But before I get on to that, let's have a look at the analysis of what this is. So somewhere here, not there, not there, not there, not there. Oh dear, where has it gone? Somewhere. Oh no, is it there? I don't know whether it's in this one. Might not be in this file. No, it is. No. Oh. Okay, here we go. So, Spectrum 10, which is actually, if I go to, there. Spectrum 10, I am looking at this loop here. Here, Spectrum 10 is on this loop. This by atomic percentage is 84.64% carbon. It actually has nitrogen in it and oxygen. And we have found that the synthesized element that you find in the flux tubes typically has carbon, nitrogen, and oxygen. And this is stellar synthesis, C.I.C cycle. Okay. And so, you know, you look those together, what do we have? We have basically 0.83% of the atoms are copper. And there's a little bit of potassium in there. Okay. And in fact, the potassium is below the sort of level at which you would generally say it's worth noting. So essentially, it's CNO. That's what it's made of. And this is the same kind of observation that we saw on the wire in the line reactor, in the crustation that was on the top of that. And if it's not just carbon, because it looks harder, then if it is hard and it's flying at some velocity, then what is this spectrum 11? Because I was looking at this spectrum, this material here, and this is whiter, and for me that normally means it's probably a heavier element. So we look at that spectrum 11 here, which is this area here, and look at it. It's got no nitrogen. It has carbon 50.687, oxygen 23. It has titanium. I don't know where that came from. And it has 21.29% copper and iron. Well, the iron might have come off the material at the bottom, and the copper might have come off because it's running through copper. Is this the material that it's chopped off as it's been passing through things, or is it material that it was in the process of assimilating at the point that the structure died? And if you look at it, you can see the band coming through here and going round. There's this zigzag structure here. And so I have two postulations for this, and you know, I'd like your opinion as to what it might be. In fact, they might both be the same thing. You've got the itonic mesh, and when the thing blows up, fragments of that itonic mesh can come off. And they might twist themselves into a contorted structure, and then they have their own spin and so forth. Or the entire mesh might collapse, like one of those toys. You know, it's like a little toy that expands out and goes like that. But if you crush it this way, you might end up with something that looked a bit like this, is my speculation. And if that is true, then one might think that this is below a solid. It's more dense than a solid. It's a super solid. But at the same time, it's coherent matter. And if you imagine this going into other metal or other material, and it is essentially made of alpha conjugates and almost entirely carbon and oxygen, but mostly carbon. You could imagine actually somehow that the gaps between here were condensates of helium. And when this comes out of, it's actually denser, but when it comes out of condensation, the helium evaporates and it just leaves the carbon shell there. Yeah? It's a bit weird to think about it, but the helium atoms, the alpha particles, just leave, and they leave an open shell here. But it's not so surprising. Like, if you remember the spider web on the coming out of the single point on the Hutchison fracture sample, it would look like it was a diamond web and on the edges of the facets of the diamond web, it had magnesium. And magnesium is double carbon. And that's also what we observed in the vortex on one of the points on the Amasa vibrator plate. You had diamond in the center, and then on the outside of that, you had magnesium in the vortex. And on the outside of the vortex of the magnesium, you had chromium. And so chromium is double magnesium, and magnesium is double carbon. And so it might be that the densest part of this, which is just an alpha condensate, is actually the gaps between here, and they get lost, and it emits alpha particles. But the shell here, I wouldn't want this thing going into my head at high velocity. I wouldn't want that. I really wouldn't. And so I think people have to be extremely, extremely careful when they are running these kind of experiments, because you just absolutely wouldn't want this coming into your head and in any part of your body. And the interesting thing is actually George Eagley has these anecdotes in his recordings that he did in the 80s and stuff from people that were exposed to ball lightning, and they described how when they were near the ball lightning, they felt this tingling in their body, not on their body, but in their body. And I can imagine that if you had 10 micron bullets going into the body, then you would feel a little bit tingly. Yeah, I think you'd feel very tingly. And actually, it's interesting because if you look at the guy that worked with TL-CAR, Ralph Ring, he describes that when they were turning on the apparatus that made the aluminium such to a jelly, so he could put his hands in without it, it was cold, but it was like a jello, and he could put his hands in and pull them out of the aluminium. That when that apparatus was turned on, he felt tingly. I don't necessarily think this is a good thing that you feel tingly. Okay, that aside, where are we? Okay, so so I have a hypothesis here that Shishkin showed, and his team showed at Dubna, that the exotic vacuum objects can grab the string vortex solitons, as his terminology, the neutral form of magnetotoroelectrical radiation, which he concedes is just like Scholder's EVOs. They can grab the atoms of the material that they pass through. But also, if you can imagine, an alpha condensate is going into a material. If it stops in that material, and you have an overlapping of this quantum condensate with the atoms of the material it went into, then you would get transmutations when everything settles out that were alpha conjugate nuclei of the material it's into or it contained in its payload when it comes out of the coherent state. And so the transmutation isn't, the Coulomb barrier is not relevant whatsoever. Forget it. Okay? This structure does not see the Coulomb barrier. It just is not there. And it can go in slowly, or it can go in quickly. It doesn't really matter. Or it can grab the atoms because they're being thrown at it. And when they're in this condensate, like this for me would explain why you see blocks of material that are transmuted. But why do we see mostly carbon? Well, I think it's to do with the intensity level of the energy. Because when you think about what Leclerc was doing, he was doing cavitation, but the diamonds that were forming on his aluminium were coming away from the hole in the aluminium. But he was producing flecks of material that had every element in the periodic table, even transuranics and so forth. And I think what that is you've got the cavitation is on the same spot, and you've got the coherent matter that's being fed energy. It's fed energy, it's fed energy, it's fed energy, and to the point that it basically explodes. But it's pushing it beyond the point at which it can mostly deal with producing carbon. And in fact, he says that you have to kind of burn the carbon. He says that you have to get under 55% carbon before you will start seeing heavier elements. And then once you do that, you go all the way up and so forth. In the case of SV Adamenko, he had a 300 joule 110C charge into a very small target. And it almost didn't matter what his material was, his metal that he started with. He got most of the elements in the periodic table, but more often than not lead. But I believe that he didn't see... Well, in fact, he did create transuranics, and in fact, he created elements that were not in our near universe. So it's about the energy concentration. And on that note, I'm now going to show you something which I found curious, and I presented in Copenhagen in 2017. And it was found on the foil, which was produced by Suhas Ralkar in his lab in Mumbai. And why I found that interesting at the time was it was a 10 micron elongated structure. And I said that this bullet might have a silver lining. Well, I'll show you why I said that at the beginning of this presentation, if you'll bear with me. So, what I'm referring to is this. Silver on nickel foil. And this had nickel sulfate or something in the electrolyte solution. But he was discharging, I think, about 2000 volts in pulse discharges to do his electrolysis. And if you want to go and look at the foil making process for the Echo reactor, you can go and observe this. But the point is that this is a 10 micron long structure, and it's about 5 micron wide. But it also has this torus-like structure here. So if I zoom into this, you can see this torus-like structure. But also, it's got these rings going around it, almost like there's one band there, one band there, one band there. This looks like the impact mark that I shared on Fast Track to Coherence that was found on the plate, the steel plate in the Amasa vibrator plate. And this is 94.5% silver. And I've got this in higher res, so let's put that in higher res so you can see it in a little bit more clarity. 94.5% silver, and the nickel is 4.1, so you can see that it, in fact, in the background, this is almost entirely nickel. And then the rest are below detection threshold. So essentially, it's nearly pure silver with a little bit of nickel, and the next thing that you can actually class as actually being there is carbon. And so what I'm saying is, effectively, that in this case, there's so much hydrogen, there's so much nitrogen, there's so much oxygen, and the intensity of the coherent matter driving process is insufficient to go beyond carbon. And so this is why when Yul Brown was taking iron, aluminium, and by the way, I'll revise my statement on the aluminium is oxidizing, it's producing atomic hydrogen from the HHO gas, and that is producing effectively binding with its small magnetic dipole to the iron, and then when you go through the Curie point, they all come off at the same point, and that produces coherence because they're the same thing, a proton, at the same energy, same de Broglie wavelength, and they cohere to form coherent matter, which forms charges of two types, north and south magnetic monopoles. They cluster into itonic clusters, and if you think about it, all LENR works this way, and I will describe how every single LENR system works this way. But essentially, how should we put this? In 2001, Matsumoto suggested he suggested that to create itonic clusters, you use a LINAC. I discussed this in my last presentation at Assisi rather. He used a LINAC to create protons. Why would you do that? Because you'd want the protons at exactly the same energy. And then he fired electrons, bunching them in order to create them to be coherent. And the two together would snap and form itonic clusters, which are ball lightning, which are EVOs, which are ectons, etc., etc. And so essentially what he's doing is creating that itonic clusters, the ball lightning. It gets to a level of coherence, and in fact it snaps when you go through the iron Curie point, which is about 1000 and something Kelvin, and then it forms the ball lightning, and the ball lightning just grabs the material. And because the ball lightning is not overdriven, it takes the americium 241 or it takes the cobalt 60 and it sucks it in, and it has this vast quantity of nucleons at a low level of condensation, but condensated all the same, with the cold neutrinos from the condensation process. And it instantaneously deals with that radiation. It basically transmutes those elements to carbon because it's not overdriving the process. In the case of Leclerc, he's driving it, 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 so he gets every element in the periodic table and pushes it way past into the radioactive elements. Okay, that is what also Adamenko is doing. And I believe that what you are seeing here is the output from a strange radiation track. This is a dead strange radiation structure, or conversely, a coherent matter traveling wave, which was a blown up itonic cluster or ball lightning fragment. And in this case, the level of coherence and the level of condensate led it to be nearly pure silver when it concluded. And in this case, it led it to be what it mostly and easily creates, which is mostly carbon. And if we go on from here in this presentation, we also had one of these strike marks, okay? And around the strike mark on the radius, we found this white area here, which was 32% gold and 7.2% palladium. What I am saying here is that if you get the right energy in your structures, you can target the synthesis of particular elements, okay? And it may aid to start with an element where you can add alpha conjugates to it so that you end up with the target element that you seek. I think that's pretty cool. That's pretty cool. The evidence is stacking up. So I've got one more subject I want to deal with tonight before I call it a day, and that is to do with magnetic monopoles. But before I go on to that, because it's really, really rather special, and I have to again thank Henk for supplying the Vega Valley to me, because it would not have been possible to have come up with that conclusion that you're going to see in a minute without having that. I'm going to look at some of your questions. Yeah, it looks like similar to a lightning fossil. Yeah, I'm not surprised. Yeah, I don't know if you recall when I was working with the Gas, and we put the Gas on the PTFE, and the PTFE got a carbon coating You can go and see the beginning, the end of the beginning, or on our YouTube channel. And I touched it to see if it was kind of like bound to the surface, and then I found this really unpleasant tingling feeling in my finger where the carbon deposit was. And so I said, look, I'm going to have to go and wash my finger. And you can see me washing my finger on the video. But I had to wash the finger. And I had a hunch to get rid of the tingling feeling that water is good at capturing this. At the time, I didn't know that the exotic vacuum objects wanted to bind themselves to oxygen. And oxygen in the water is suitable to doing that. And I've explained that all since, having realized that and read the work of Oraitzkiev. But I do understand that if you were to use this technology in, let's put it, negative ways, that if you wanted to clean up the site where this technology had been used, you would put a water feature there. And over a period of decades, it would decontaminate the ground from use of this technology, and that's all I'll say about that. So when I felt this tingling on my finger, I had no idea that I would go on to find this and realize that this is a dead coherent matter traveling wave structure, or a collapsed part of an itonic mesh from a ball lightning, Evo, whatever you like to call it, ecton. And so I had no idea that I might be exposing myself to things that look like this, or like this one over here, which was silver. But I expect that the one that went into me was carbon, because it was driving off the fluorine. I mean, it could have also been some breakdown product of the PTFE, which was producing hydrofluoric acid. Maybe that's possible. That is possible. But I have to say that it didn't feel like it was burning, and I didn't have any chemical burn on my finger. It felt like the tingling was inside my finger. And so that's why I had to wash it off there. And so I genuinely think that this is a real thing. Actually, Corky, it wasn't me putting my finger under the gas. It was the gas exposed to polytetrafluoroethylene. In fact, I have the piece of PTFE behind me somewhere. And I touched it with my finger, and you can see a smudge on the PTFE. But everyone's touched carbon, like you've touched a graphite drawing pencil or something, like a charcoal when you're doing charcoal and chalk artwork. Everyone's touched that at some point in their life, but so I knew what touching carbon and charcoal it feels like, and this didn't feel like that. It felt like there was tingling going into my skin. Like, you know what it felt like? It felt like being stung by a jellyfish, and it was unpleasant. And I knew I could see and have observed there was something anomalous with the gas, and I didn't want that on my finger. I just wanted to get rid of it. The Russians done a lot of work on effect on humans for EVOs. So I think it's Pryakin. I think he's done work on, their team have done work on the effect on plants, and also effect on, the Russians have done effect on work on mice, I think, and also other organisms. I felt like I touched a weak electric fence when my pinky ting. Okay, all right, interesting. Yeah, I did put my hand in to the flame, and certainly for the time that I passed my hand through the flame, it didn't feel, bad. But uh, the touching of the carbon. Now I understand that this these exotic vacuum objects, they love carbon. Yeah, it is that. In fact, I think I have the phrase here where, is it in this one? I think it's in my. Wait, I'll find it. No, my machine's gone slow because I've loaded up something else. It was in the Lena in a Can presentation. I think it was under, yeah, so this is a very early slide. So it's actually a slide from Mode. But I've used it many times. This is what Leclerc said in an interview. Oh dear, my machine's just frozen. Oh, there we go. Right. Leclerc said this in an interview, which is now not on YouTube. But he says it must burn carbon first. When you get less than 55% carbon, iron and higher elements appears alpha steps. So what I'm suggesting is, since we know that from Shishkin et al.'s work, that whatever element you use, the exotic vacuum objects in the string vortex soliton form, the neutral ones that I believe you saw passing through that metal earlier in this presentation, they will capture some of those metal ions, they will incorporate them, and if they've got alpha conjugate nuclei, alpha nuclei in them, they will synthesize elements that are based on the initial element and the element and carbon nuclei and alpha steps. So he actually said alpha steps here, right here, and this is also what SV Adamenko says. He said that you produce alpha conjugate nuclei, and so my observations in the Amarza gas on titanium versus PTFE are not surprising in that context. But the beauty of that experiment is, one, it's very short. Two, it showed alpha conjugate nuclei on titanium, and it showed alpha conjugate nuclei on fluorine. And why that is brilliant is because the alpha conjugate nuclei on titanium don't necessarily show bosonic or fermionic nuclei, because titanium has both. But it does show that you can get all the elements from titanium up to titanium plus carbon. In the fluorine case, that is a fermionic nuclei. So it can show that it can grab fermionic nuclei and then combine it with alpha particles in the case of sodium and aluminium and chlorine 35, I think it is. Anyway, is it chlorine? No, phosphorus. So you get 19 fluorine goes to 23 sodium, goes to 27 aluminium, goes to 31. Is it 31? I don't know. I think it's 31 fluorine. But anyway, it might. Yeah, that's right. Is that right? I don't know. I may have got that wrong. But anyway, it's producing alpha conjugate nuclei off the 19 fluorine. So he's saying you have to burn the carbon, and what he was finding is that he was getting a diamond film easily produced on his aluminium, and so the water and the hydrogen in the water was somehow synthesizing diamond. And diamond, what is diamond? Well, it's carbon, and I believe that is what this is. This is a diamond structure, and it has kind of diamond-like geometry here, but you've got to remember that this is a coherent matter structure, so it's not growing in the normal way that carbon would. It's in its wave structure on a macro level, and then when the coherence dies, it's when the music stops, it just ends up being what it was in exactly that space in time. And it kind of re-emerges into the normal 3D world, where it can interact with normal atoms on a kind of electrostatic basis rather than a oscillating monopole basis. Okay, so I'm now going to do the bit that I want to talk about with regard to monopoles. And so I think I'm going to show a number of slides from the first presentation that I gave at, no, maybe the second one. The second one. Okay, so I think the important ones to show here probably are this one, which I've shown many times before, and thank you to the Lion author for this. And this is, I call this the canon, and basically this is your north, your south, and this is the material that was in the flux tube, and there's a little squiggle of it again. So you can see this material came out of the coherent state, and it's like a perfect curve, right? But it's comprised of, what is it comprised of? If I click here, I can see what it's comprised of. It's in spectrum 19. Okay, spectrum 19, it's got copper and oxygen, well, it would do. It has aluminium, but it has zirconium in there. And silicon. So it's, you know, zirconium is a very high melting point element, and yet it's mixed in with these other elements. And zirconium's not in the Lion reactor, and so that's interesting. So I believe that that was synthesized in there. So today we've shown you coherent matter in the form of carbon that I think was produced, and silver in the plasma flow discharge work of Suhas Ralkar to produce the foil for his electrodes in his echo reactor. And here in the Lion reactor on the cupric oxide on the outside, cuprous oxide, there are these magnetic monopole structures that are shifting material around. And so this is Perovskikov, this is Bogdanovich, and this is my hypothesized structure based on this being a 3D structure, and you're just seeing 50% through it. Why are you seeing 50% through it? Because it only goes 50% into the material, like normal. Now this next slide is probably one of the two most important slides that are needed context-wise to understand what I'm about to show you that was observed on the Vega Valley. And what we've got here is, oh god, I've got the same video in multiple places, but I've actually stopped it. So I'm going to go backwards and forwards. Okay. I've done this for imaging purposes when I print it, so you can see everything. So, oh no, it doesn't actually show that on the slide. That's interesting. Okay, so you're going to see it 4 times, but essentially the one pole has a hole in the middle and the other pole has a spot. Okay, and up here you've got 2 spots together, and down here you've got 3 holes together, 3 holes. So if let's call these, I don't know, they are south monopoles because they're pulling material away from the surface, and so they leave this hole in the middle. But note that they can join together in chains. They can join chain together or pairs. There's a pair up here. This is a chain. Okay, so the norths can join the norths. Okay, and I think this is very important for what you are going to see. And on the end, I think it was, of this video, there was this structure, which is, in this case, this is 2 south poles joined together, and in this case, it is 2 north poles to join together. And I believe the one that you're seeing here by Solin was, I don't know, this is probably 2 north poles, actually. Because, look, you can see that it has the line around the outside and the things coming in here. So the line is around the outside and it's coming in there. This is going the other way round. So it's showing the opposite rotation. So this is showing the rotation round to our right, and this is showing, well, it's still showing it round to the right, but anyway, it's around the other side, I guess, if you rotate it. Anyway, I believe that this is one type of rotation cluster and this is another type of rotation cluster, and you can always tell one of them because it has this band in between where you get the interference between the 2 structures. Anyway, this is the same with the soliton cluster in Solin, and I believe that that this particular artifact from Iraq was a how shall we call this? It's evidence of weapons of mass destruction. Let's put it like that. And what you see on the top here, I'm going to actually blow that up. So, well, I'll make a new slide here, and I'm just going to make it blank apart from that. And I'm going to make it blank. And the reason I'm doing this is because I want to show you that it has around the outside this structure that Solin says in his patent is due to alternating north and south magnetic monopole structures. And his drawing that he drew in his paper, in his 2001 patent, is on the right of this frame that I'm about to show you here. So you have the zigzag here, okay? And there's 2 rows. This may or may not be important, and I'll show you why in a minute. And you have the zigzag here, okay, with the point. So this would be a row of norths, this would be a row of souths, this would be a row of norths, or vice versa. It doesn't really matter, okay? And you get material flow in a direction. Like I showed you material flow here around the outside, and I showed you material flow, oh god, in the other images, wherever that is. I showed you material flow here. So like I showed you material, sorry for all the videos here. You've got material flow around the outside, okay? So I believe that maybe what he's suggesting here in this particular sketch is that there is material flow in a direction this way, and there's material flow in a direction this way, and these can all be norths and these can all be souths, okay? Maybe he's thinking they're arranged this way, but whatever, you're going to see something very similar in the Vega Valley. And just one other thing, these 2 rows that you just saw, I can't help but think they remind me of the structure here, where we've got a north and a south effectively, and you've got 2 rows of fluffy nanocarbon on the outside of this structure. 2 rows around the outside of the structure, and this would be, say, a what is it? Is this the north or that's south? Oh, well, it doesn't matter. One's one and one's the other. Okay. All right. So there's that. So now I'm going to show you the cover slide of this presentation. In fact, I'm going to actually get the image because I produced it at 4K, and we will have a detailed look at that. Okay, so I need to first give you an overview of the whole thing. Is it this one? No, it wouldn't be, would it? It's not that one. Talk amongst yourselves. Nearly there. Okay, all right. Okay. So this is an overview of the Vega Valley. Okay. And the area that we are going to focus on at the moment is not all these carbon ejecta on the outside in the double there. No, we're not going to look at that at all. We're going to look at this area here where you have the main channel that was between 2 brass plates that were either side of the main channel, and you had the main bond lining forms, and this in my view is producing fluidized electrons, and they are flowing out from the production zone of the fluidized electrons in a structure that is a magnetic fluid which has a facial structure that's equivalent to many itonic meshes joined together. So it effectively looks like magnetic fluid with a kind of buckyball structure, but it's actually like a sausage. And we're going to look at this area here, where we come down here and we're going to come out to this area here. So it's the end of a floodplain. And so you can imagine that the intensity is less down here, but it's got some very interesting things that I think are we need to look at in context with what Solin shared in his patent in 2001. So this is a scaled image of the area in question, and I was using this to show that this is 7.5 millimeters across and this is 5 millimeters down in the field of view. So it's a little bit bigger than that, but the reason I've got these endpoints is that this red points are the extremities of the field of view of the alpha camera. And so I was calculating the number of microns per pixel in the Sony Alpha camera. Now, what I also did was I looked at this, which is 3 of these groups, okay? And 3 of these groups has a, what is it? 617 micrometers for 3 of these large groups. So one group would be 200, and 200 is like, I don't know. But anyway, these are the kind of large groups that we have on this area of this tongue here. Now we're going to go down to this area over here, and I've got a composite image. But before I go, I've got a composite image. Let's look at that. And we will look at that in Photoshop because it's really rather large. It's just easier to do it there. So here we go. All right. Now, the thing I noticed when I originally looked at the image from the this was there seemed to be some polarized banding. Red on the end as a cap, green around the outside, red, green, red, green. Polarized, okay? So I wondered how big these were, and each of them are approximately 50 microns across. And I thought, well, that's interesting because that's the sort of size of an Evo, really, radius. So radius is 50. This is 100 microns across. So if I had, a red, green, red, green, red, green, that would be 600 microns. Well, you know what? That looks a lot like what we are seeing here. 617 microns for a group of 3 large structures. Over here, this is, if you imagine 6 of them, that would be essentially 50.49 times 2 times 3. So it looks like whatever created these structures is the same kind of thing that created these, and they come in pairs. Yeah, these ones are 200 and a bit per piece on average, and a pair of these is 200 and a bit. Okay, and we've already shown in this slide here that south and south can join together, and north can join together. And in fact, not just 2, but we showed in this slide that you can have 3 joining together. So this is, God, what is it again? North and north and north, and we've got south and south together. So you've got 3 norths joining together there. So you could imagine that they would keep on joining together, and then you could have souths joining together next to them, And this one would be spinning one way and one would be spinning the other. And what would that do? Well, you know what that would do? Is it would create circularly polarization of light. Now the question is it created some change in the material such that it's created the circularly polarized light? If I go back to here, you can see that on the Sony Alpha image, it's much more clear. And in fact, you can almost see the circular but also slightly hexagonal outline of this. So they're kind of like offset from each other. So this one would be one pole and this would be another pole. This would be another pole. And so I believe that what you are looking at here is alternating magnetic monopole rings and bunches of them together. And you can almost see the ring with the spot, ring with the spot, ring with the spot, ring with the spot here. And so you can see this, you can kind of get an idea of what this surface of the structure is and why it lends itself to producing those kind of surface structures on the overall material. The kind of like what I call the kernels, the kernels from sweet corn or maize. Yeah. So I will come to talk about, and I'm going to put a challenge out there. Why is what I'm showing you here absolutely earth-shattering? That's the challenge I'm going to put out there, and I'm going to put out probably some presentations of the implications later in the week. But I just want to see if people can guess what it is. If people have been following this far, they should know what the implications are of what I'm showing you here. It's going to be a good several hours, and I haven't got time to do it today. But I want to give you the fun gift that I wanted to give to the people at Assisi, which I'm almost more excited about than finding the polarization of this material. And you'll see why in a minute. But as I said, the polarization scales and the alternate banding matches the structures further up the channel that are formed on the walls of the Vega Valley. And I believe that this matches very well if you can imagine those itonic clusters joining together and wetting together, just like you saw in the Vega experiments where you had the balls of lightning and they wet together. You can imagine that they are these meshes, that the mesh that I showed you on the inside of that structure that was consuming and transmuting the copper in the SEM that I was showing you earlier. And this is how you get the disruption of material. In the case of Hutchison, he saw like circles coming out of the center of pieces of iron or whatever, but you would get transmutation. So I'm saying that this structure that's eating the material, they can wet together and form chains, and then those chains can wet together and form bigger balls, but always on the inside you have this kind of itonic mesh type cluster. Now if you get two of them together and they squish, then they would form these channels that you're seeing in the Vega Valley, and the overall structure would have this kind of 5-sided, 6-sided geometric nature, a bit like a kind of carbon allotropes, as I've been saying for a very long time. So this for me was just a completely amazing. And when I realized that Solian was essentially describing what this is, and we've already shown the evidence of how these singly poled monopoles can join into chains, then I think all the evidence is lining up. So I have one gift for you today, and this is probably the thing I'm most excited about. And it's on the scanning electron microscopy here. Which, by the way, when I show the elements here, it doesn't show anything other than copper. Okay, copper and oxygen. And so, well, maybe a bit of carbon. But anyway, in fact, maybe I'll dig that up just to confirm it. I don't want to say something wrong, if I can avoid it. Where are we? Here. And no, it's not there. Down there. And it is Vega Valley. And it is in our wonderful... oh, did I not do it? Oh, maybe I didn't get time to do that. Oh, have I not got it? Where has it gone? No! No, I've definitely got it somewhere. Don't go away. No, that's not it. Okay. Well, you'll have to take my word for it at the moment because I can't find out where it is. But what I want to show you is something that is in this area here. And bearing in mind that this is 11 months old, are you ready for it? Are you ready for it? Are you ready for it? I'm going to zoom in now. I'm going to zoom in. What are we seeing? Oh my God, what are we seeing? What are we seeing? What do you think that is? Who's going to guess? Anyone got a guess? What do you think it is? Yes, Corky! I think we have an Evo on this 11-month-old sample. I think we have an electron condensate living and breathing. And we have the ability, given the fact that this is at the... oh, you can't see it here. Okay, this is 500 micron. So I think this is 50 micron. And I think this is... I think it's about 10 microns across. I can confirm that another time. But I believe that this is an Evo. And if it is, so the first thing I want to do on the SEM, I can go into this maybe 10 or 20 or 30 or 40, maybe even 50 times magnification. Already, this is verging on being the highest quality Evo recorded in history. At 10 times this resolution or 50 times this resolution, it might just be spectacular. I'm a little bit worried when I fire the electron beam at it, what it might do. It might jump off, it might blow up, which would be worrying. So, yeah, I might need an insurance fund for that. But anyway, it's quite interesting in my view. It seems to have a trail going off here. I don't know, but... that is very, very interesting to me. But what is more interesting to me, even than finding an Evo 11 months after this sample was generated, is what I'm seeing over here. Over here. If this is what I think it might be, this is its evil twin. This is its evil twin. Is that a black Evo? And you can see it's kind of like snake trail across the surface. So I don't know how fast this is traveling, if it is traveling at all. But are they traveling as a pair? There seems to be a kind of snake trail behind this one. I don't know. The interesting thing is both of them seem to be sucking light from their surroundings. Now, normally something that gets charged will glow brightly and leave a band across the SEM. Okay, this is going brightly, not really leaving a band, but it seems to be sucking the light from around it. Okay, this one, the black one, if that's what it is, and obviously it might be just an artifact, but it is almost the same scale, but almost with a white spot in the middle. This also seems to be sucking light from around it. which is interesting in its own right. But do we have an Evo and its evil twin? And are these quantum entangled? I don't know. But I'm so excited to get under the SEM and see if this is what it might be, because this would blow the Moscow Nuclear Physics Research Institute's image of the 2-day old plasmoid out of the water, because this is 11 months later. And it would be a huge credit to Henk for leaving this running, I think, for about 100 hours in order to create such stable EVOs. And it would also be an absolute testament to Ken Shoulder's claim that these things can live in metals indefinitely until he intentionally blew them up. And I hope I'm not going to intentionally blow this up, because I imagine its payload is carbon, and I imagine its payload is also copper and zinc. But this for me, even more than finding the polarized banding almost certainly created by the alternating monopole bands in this particular area. This for me is one of the most special things I have seen in my life, and I've been pretty lucky of late. And so it's literally like a spaceship has landed. And isn't that something? I think that if we get a very good look at this, we'll know exactly how to build a flying saucer. The geometry of this will be exactly what you need to build a flying saucer, without a shadow of a doubt. So there we go. That's probably where I'm going to leave it tonight. If there's any more questions, I'll take them. I'll take some brief questions now, and if you'd like to go to remoteview.icu and comment in the blog. But for me, this graphic here with the same scale structures as are forming the kernels on the Vega Valley walls, and this polarization of light, the implications of what you are seeing here are earth-shattering. They are absolutely earth-shattering. I cannot... There's technologies out there I know you guys want to get delivered, and this is telling you that they can be delivered. It's just amazing, and nature is doing that. It's doing that, and this one sample is so amazing. Thank you, Henk. It's just so amazing. And if this is what I suspect it may be, given the history and what we have seen on this sample and the history of what we have observed over these last few years, if that is an Evo 11 months after, oh dear, now my machine's basically doing what it likes. Come on, do what I want you to do, please. If this is an Evo 11 months later, I just have no words for it, really. And I've got plenty of words, but it would just be the most amazing thing ever. Most amazing thing ever. Oh dear. There we go. So I'm going to see if you've got any questions, and then I'm going to call it a night. There we go. What a special thing that is. Okay, so yeah, Tesla. The thing is, I hadn't seen most of this stuff. I had the pleasure of knowing a little bit about Tesla, not a lot. But I'd seen enough by the beginning of 2017 that I could see what the technology could do. So it's not surprise to me the claims that Tesla made in the late 1800s, early 210s, so up to 210s, because it is the God's toolbox, and almost everything spins off this. They can't keep it in the box now. You guys out there, you are the people that know. You know that this is going to happen, and it's so exciting. It's so exciting. Sometimes it's all I can do to not get overly excited about it. Like, you know, God, if I had my own SEM, I'd be sitting looking at this sample millimeter by millimeter, And if this is an evil twin of an Evo, like this is a positron based. When I say it's not, this may not be a black Evo. This might be a positron based Evo, and this is an electron based Evo. And you know, like the Burke currents are, you have the positron and the electron, like the filaments and so forth. Those kind of twisted filaments, and like we've shown in the strange radiation tracks here. I mean, I feel like I just feel lucky. I just feel lucky that I've had a chance to look at these samples and see things in there. I mean, not just this, for the Lion, and for Echo, Suhas Ralkar's work, and for John Hutchison's work, and that you guys have helped make that happen, really. And I mean, the implications of what I've shown you several things today, where if they bear out and they are what the Solin and Shoulders effectively claimed, and Matsumoto, you know, if they are what it looks like we're seeing, it's just mind-boggling. It's just mind-boggling. Just mind-boggling. How would one manipulate a vessel's spatially? Variation of capacitor plates and oscillation frequency. Anyway, I'll talk about all that later. I just wanted to get the stuff in the background first, really. With a name like Vickers, you're the right person to be creating flying vehicles, James. Yeah, this is propulsion at any point in the universe. I'll talk more about how that and how it can probably relatively easily get to 0.8 at the speed of light. So the Russians were right that were debriefed in 1992 by the CIA, and I expect that Bostic, when he claimed you could get to Mars in 4 hours with the application of plasmoid technology, was not lying. Yeah, my challenge is right now with this technology is that if you can go from any point on Earth to any point of Earth on Earth in a few minutes, then they would have to find some method of tracking everybody and making sure they knew where they were and preventing them from using particular devices that allowed that transport before they released it into the public. And I think that's sick. I think that is sick. I think this has been held back long enough. Thank you very much. And you guys out there, you've got to be the vanguard of this. You've got to be the vanguard of this. This is real. This is real. This is the God's toolbox. And it is our birthright. And I'm pretty certain that we've used this technology as a species on this planet before, and probably how we got here. Yes, Axel. EVOs can go dormant and remain indefinitely. And I think what we're going to show, possibly with this particular sample, is that I hope I don't blow them up. That's my issue. I don't know which one to fire the E-beam at first. The positronic one, if that's what it is. the one up here is this, if this is the positronic one, or should I? Because I mean, this is effectively antimatter. if I'm firing electrons at this, we should get 511 keV photons coming out of this. So it could get a little bit interesting. I'm almost more comfortable firing the electron beam because I've already done it here and it seems to have survived. So, you know, it may be that the energy of the E-beams that I'm firing at it aren't sufficient enough to disrupt it. It's sufficient enough to get captured by the condensate. Yes, I know it's already. I'm kind of like saying rhetorical questions here. Um, Certainly with the coherent matter, I believe that ball lightning tells us what we need to know because it's able to carry around gallons of water without boiling it and sand without sintering it and float in the air, which implies that it's at the very least preventing the mechanism of gravity applying to the material that's contained within it. It's not so much anti-gravity necessarily as propulsion that you can directly apply. Anti-gravity is useful when you've got gravity. But traction through the medium that allows gravity to impinge itself upon other matter would apply also in other parts of space. Gordon, this is a dawn of a new era. And Ken Shoulders, go and read what Ken Shoulders said in his writings, and you can easily see. You can easily see why he could see these things, even with the fidelity of images that he was able to capture. What you need to do is you need to take a picture and you need to think about why the things in that picture are where they are. Nature does not lie. What you see is the answer to nature. it's as Piantelli said to us in 2015, don't tell nature what it is, let it show you. And the only way it can show you is by showing you what it did. And we have the pleasure now with very cheap cameras and the work of Hank and Dave, and that collaboration has just been absolute joy. Thank you guys again. I can't thank you enough. But you know, and by the way, if anyone wants to help, Hank wants to get some gas. He wants to get some nitric oxide that I identified from, and some HF4, I think it is, for testing to see if that accelerates the process. So if anyone wants to help us with purchasing that, that would be great. But already, I think so many questions are answered with this one sample. When Henk sent me that sample, it's almost the only sample I wanted to look at. No offense to other people's samples, but I knew it was special when I looked at it under the Narugo lens a while back. Well, James, I think there's going to be whole industries. As I said to the people at Aarhus, I think there's going to be whole universities that are dedicated with different departments to investigating aspects of what this technology can deliver. Good night, Slobodan. Oh, great. Thank you. I'm looking forward to seeing your samples. I've got, like I say, I've got another Microscope session in a few days. I've got something exciting to share that looks like it was found on the another part of the calcium oxide that we exposed, and so I'll probably do a presentation on that later in the week. So in most videos, Thor's asking, are the presentation slides from previous years available? In most videos, the presentation slides are available as a download from the description of the video or from either Steemit or Remote View. The presentation slides I went through today, and in the third session in Assisi, I will put up a selection of slides from some of the more freeform stuff that I did at the end here, including the one that you see on the page here. But that might be a day or two away. Wow, I just feel so lucky, just so lucky. So bye, Slobodan. Have a great week, and I know you've got morning work, so. I think anyways, John Watson, that an Evo can be created, it will, but essentially electric discharge kind of does it, or moving electrically charged particles will do it. So I'm going to do a very brief summary of what we saw today. So we saw, oh God, what did we see? We saw a lot of things. We saw a vast array of strange radiation tracks that I believe explain all of the observable witness marks that have been observed since 1992, when it was first observed by Solin, and he, I believe, mischaracterized them as a shockwave from the explosion of a quantum coherent reactor unit. However, it is something that comes from that, and so the characterization of where the track came from is from that particular event. I think that we observed the dead product from a number of different ejector, and we discussed how the level of energy concentration and the level of carbon that you've left in your material will lead to a point where you have particular elements synthesized or not, and that I think we proved that it is an alpha conjugate nuclei with the titanium and PTFE and Amasa gas experiment alone. I think that we proved that the structures on the inside of the line reactor are monopoles, and that they are of two different charges, north and south, and that they are able to sweep and manipulate matter, and they are able to group in pairs or more of the same type of monopole. And then with the Vega Valley, we have been able to show, I believe, that they are able to cluster into large magnetic fluid, alternating magnetic monopole, alternating monopole magnetic electrical fluid condensates, and that these are able to polarize copper such that you get this beautiful green and let's see if my computer's cooled down enough to sweep this out there, this beautiful patterning here on the copper on the Vega Valley, showing this banding produced, in my view, by the monopoles in bands, and that this was, in my view, accurately described by Solin, and that the scales is standard sort of Evo scales, and that they are the same scales that produce the structures, the kernels. And then I think the last thing of note is that we may have found an electron and positron based Evo pair on the Vega Valley floodplain, as you might like to call this little tail end here, where we have these monopole structures. And the exciting thing for me is to be able to go and see if these are what they have the potential to be, and to go and look for more of these bullet-like structures that I believe are the dead remains of strange radiation. And I would like to look in more detail at the structure inside an impact mark, which I believe may be showing the itonic mesh, which may be what causes these strange radiation tracks that we witness. So I think with that we're pretty much done, and I think I pretty much got a generalized understanding of how LENR occurs now, and we can walk through that, and then we can get on to some more interesting stuff like anti-gravity and stuff. But I think it's going to become very clear what people need to do synthesis of the elements. It's going to become very clear what they need to do to produce energy. We're going to talk about free-floating fireballs and how why that's important. Oh yeah, we also talked about in this presentation how we've shown on a macro level in the Vega experiments with Henk and Dave, how you can get self-organized electron clusters, these balls of fire as they were referred to in 2001, and how they can wet together, and that we see what appears to be, and I will do further work to confirm the hypothesis which looked tentatively to be revealed in the cracks and inclusions in the copper, that this is actually really what's going on, and that this is how the disruption of material would probably have occurred in the 1990 paper of Takaaki Matsumoto and the 1979 work of John Hutchison onwards. And so I think we're getting close to understanding the disruption of materials of John Hutchison in totality. I think you're starting to get a hint of where the lift can come from, and I'm going to probably deal with that as we move forward in a little bit more detail. Okay. So I think the takeaway here is I have been contacted by Italians, Americans, including people working on the Sapphire project, and Chinese within 2 days of me leaving Italy, and they're all taking it very seriously. And so I think people that are not taking the work that's coming out of Vega and the Solin patent and the proclamations and desires of the US Air Force spanning at least 65 years, probably more like 73 years, that you've got to take their desires to look at ball lightning seriously. They're not doing that for guesswork, and they specifically said in that 1993 submitted paper to Fusion Technology that really nature is showing you what you need to do this, and the rest is just, in my view, wasting money and time. And no one should be wasting their lives. I don't really care how it pays the bills. No one should be wasting their lives doing something completely fruitless, because there's nothing more precious than life. They shouldn't be doing it. They should be picking their nose or lying on a beach and doing nothing, rather than wasting their lives on a completely fruitless endeavor. And I think you all know what I'm talking about. And likewise, these have been weaponized, and it makes me sick to think of that. But I think you can understand from what I've shown you today how obvious it was to Ken Shoulders how this could be weaponized, and it has been, obviously. And I've shown you where that's obviously been discussed and so forth. But let's use this for what it can do for good, and let's not pretend and be part of the lie that this doesn't exist. Are we going to be a footnote in someone else's presentation 100 years from now, just as Tesla is for many people's presentations now? I mean, many things weren't discovered when Tesla was around, but he said in 1911 that I can we're using this principle. I can create a device that has no planes or control surfaces or screw propellers of any kind. It can be any shape, and it can carry any weight, and it can travel at fantastic speeds in any weather. In 1911 in the sun, New York. What do you think he was talking about, guys? What do you think he was talking about? And the Wardenclyffe Tower wasn't an energy transmitter alone, it was an energy generator. And that will be so obvious to you. It's going to be so obvious to you. It's going to be so obvious to you. Okay, so I'm going to probably call it a night. So thank you and you know, let's hope this delivers. But if it doesn't matter, you know. But I don't have another explanation for why something would be so perfect, unless it's a self-organized structure. And it looks pretty similar to, you know, what you might imagine the structure would look like. So there it is. There it is. And if that is the positronic evil twin, the antimatter structure over there, then wow. Wow. And what I'm showing you here, like the implications of this polarized structure, just when you grasp what the implications of this are, it's just phenomenal. It's just phenomenal. All right. So, arrivederci. Buenas noches. Dobra noc. Bonsoir. Arrivederci. I might have said that before, but I've been tired this week. Thank you, and I'll see you soon.